sleep, and study. Don't forget to subscribe. Welcome to a journey that will shatter everything you thought you knew about reality. This isn't just another physics lecture. This is a descent into the rabbit hole of quantum mechanics, where reality becomes a choose-your-own-adventure nightmare that even the most brilliant minds struggle to comprehend. Imagine a world where particles can exist in multiple places simultaneously, where observation itself can change the fundamental nature of reality, where the line between possibility and actuality blurs like a watercolor painting left out in the rain. This is quantum physics, the science that makes science fiction look like a children's bedtime story. Let me take you back to a time when the world of science thought it had everything figured out. The year is 1897, and the scientific community is riding high on the wings of classical physics. Scientists like Maxwell and Newton have painted a picture of the universe as a massive, predictable machine. Everything can be measured, predicted, calculated with mathematical precision. The universe is a clock, and humanity believes it has the key to understanding every single tick. But beneath this confident exterior, dark clouds were gathering on the horizon of scientific understanding. Dr. Elara Winters was not your typical physicist. With wild copper-red hair that seemed to defy gravity as much as her theories defied conventional wisdom, she stood at the precipice of a scientific revolution that would make most established researchers run screaming. Working out of a modest laboratory in the misty highlands of New Caledonia, Winters was about to challenge everything humanity thought it knew about the nature of reality. Her journey began with 3 seemingly innocent experiments that would become the nuclear bombs of theoretical physics. The first was the quantum dance of light and matter, an experiment so bizarre that it would make even the most stoic scientist question their sanity. Imagine light behaving sometimes like a wave, sometimes like a particle, switching its fundamental nature faster than you can blink. It's not magic, it's quantum mechanics. The second experiment involved the quantum entanglement, a phenomenon so strange that Einstein himself called it spooky action at a distance. 2 particles become so intimately connected that measuring the state of one instantly affects the other, regardless of the distance between them. It's like having twin siblings who always know what the other is thinking, except these twins are subatomic particles separated by light years. The third experiment explored the probability waves that underpin quantum reality. In the quantum world, particles don't have definitive positions. Instead, they exist as probability clouds smeared across space and time, like an impressionist painting. A particle isn't here or there, it's everywhere and nowhere until someone looks at it. These weren't just scientific curiosities. These were fundamental challenges to our understanding of reality itself. Dr. Winters knew she was treading on dangerous ground. Her colleagues thought she was mad. The scientific establishment looked at her work with a mixture of confusion and contempt. But she understood something profound. Reality is far more fluid, far more mysterious than anyone had ever imagined. As she would later write in her groundbreaking journal, the universe is not a machine. It's a living, breathing ecosystem of possibilities, where observation creates reality, where certainty is an illusion, and where the only constant is beautiful, terrifying uncertainty. This lecture is a journey into that uncertainty, a roadmap through the quantum wilderness that will challenge everything you believe about existence. We're going to explore how particles can be in multiple places at once, how observation changes reality, and how the fundamental building blocks of our universe operate on principles that make science fiction look like a documentary. Prepare to have your mind completely and utterly fucked. Are you ready to fall down the quantum rabbit hole? The year 1897 wasn't just another moment in scientific history. It was a time of unprecedented technological revolution and intellectual hubris. Across the globe, scientific institutions buzzed with an almost palpable sense of completeness. The great scientific minds of the era believed they were mere inches away from understanding the entire universe, a cosmic puzzle they were confident they could solve with nothing more than classical physics and sheer human intellect. In the grand halls of scientific academies, from London to Paris, from Berlin to Cambridge, brilliant minds gathered in mahogany-lined rooms, smoking pipes and discussing what they believed were the final chapters of scientific understanding. Professor Heinrich Rothmann of the Berlin Imperial Academy of Sciences would often declare during his lectures, "Gentlemen, we stand at the precipice of total knowledge. The universe is but a clockwork mechanism waiting to be fully comprehended." Little did they know how wrong they were. The scientific landscape of the late 19th century was a carefully constructed edifice of certainty. Classical physics, born from the work of giants like Isaac Newton and James Clerk Maxwell, presented a universe that was predictable, measurable, and fundamentally understandable. Every phenomenon could be explained through precise mathematical equations. Motion, energy, light, all were thought to be perfectly comprehensible through a deterministic lens. But beneath this veneer of confidence, strange cracks were beginning to form. Take the problem of black body radiation, a seemingly innocuous scientific puzzle that would become the first tremor of a coming intellectual earthquake. Imagine a perfect absorber of light, a theoretical object that could capture all incoming radiation. Classical physics predicted something impossible, that such an object would emit infinite energy at high frequencies, a mathematical absurdity that came to be known as the ultraviolet catastrophe. It was like predicting that a kettle would spontaneously explode with infinite power, defying all known laws of physics. The scientific community was wrestling with a collection of experimental observations that simply didn't make sense within their existing framework. The photoelectric effect, where light striking a metal surface could eject electrons, behaved in ways that completely contradicted classical wave theory of light. Bright line spectra from heated elements showed discrete, specific frequencies of light that couldn't be explained by existing models. These were not minor discrepancies. These were fundamental challenges to the entire understanding of physical reality. Dr. Elara Winters understood something her contemporaries refused to acknowledge. The universe was far more mysterious than anyone imagined. While other scientists saw these anomalies as minor irritations, she saw them as doorways to an entirely new understanding of reality. Her colleagues would mock her, of course. Probability waves, particles that exist in multiple states, observation, changing reality. They would laugh, puffing on their pipes and adjusting their waistcoats. But Winters knew she was on to something profound. The scientific establishment of the time was like a massive, rigid structure. impressive in its complexity, but utterly unable to bend. And when reality doesn't fit your understanding, something has to break. Either your understanding changes, or your entire conceptual framework collapses. In research laboratories and academic institutions around the world, a new generation of scientists was beginning to ask dangerous questions. What if the universe wasn't a predictable machine? What if reality was fundamentally uncertain? What if the very act of observation changed the thing being observed? These were not just scientific questions. These were philosophical hand grenades, ready to explode the carefully constructed worldview of an entire generation. Dr. Winters had a unique perspective. She understood that science was not about certainty, but about continuous questioning. The moment we believe we know everything, she would later write in her groundbreaking treatise, is the moment we stop truly understanding anything. The stage was set for a scientific revolution that would make the Copernican revolution look like a minor disagreement. The old guard of classical physics was about to be challenged by a new understanding of reality, so strange, so counterintuitive, that it would make science fiction look like a documentary. Quantum mechanics was coming, and nothing would ever be the same again. The prevailing perspective of scientific understanding was about to be brutally dismantled, piece by carefully constructed piece. For generations, scientists had built an intellectual framework that treated the universe like a grand, predictable machine, a cosmic clockwork where every gear, every movement could be precisely calculated and predicted. Dr. Marcus Holloway, the most respected physicist at the Royal Scientific Society, represented this dying paradigm perfectly. With his impeccably trimmed beard and steel-rimmed glasses, he embodied the classical scientific worldview. During a lecture in the winter of 1899, he famously proclaimed, "Gentlemen, we are mere steps away from comprehending the entire mechanism of the universe. All that remains are minor refinements in our mathematical models." How spectacularly wrong he would prove to be. Preparing and narrating this theory took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the theory. The classical perspective assumed a universe of absolute certainty. Every particle had a definitive position. Every movement could be tracked with mathematical precision. Time was a constant, unbending river. Space was a fixed, immutable stage where physical interactions played out their predetermined scripts. But reality had other plans. Consider the fundamental assumptions that formed the bedrock of classical physics. Newton's laws of motion promised a world of perfect predictability. If you knew the initial position and momentum of every particle in the universe, you could theoretically calculate every future state with absolute precision. It was a deterministic dream, a universe where free will was nothing more than an illusion of incomplete calculation. The first cracks in this perfect model began to appear in the most unexpected places. In laboratories across Europe, scientists were encountering experimental results that simply refused to conform to their existing understanding. The behavior of light became particularly problematic. Sometimes it behaved like a wave, spreading out and interfering with itself. Other times, it acted like a stream of discrete particles, each with its own independent trajectory. This wasn't just a minor scientific curiosity. This was a fundamental challenge to the entire understanding of physical reality. Dr. Elara Winters understood the profound implications better than anyone. While her contemporaries saw these anomalies as mere technical problems to be solved, she recognized them as symptoms of a much deeper mystery. The universe was not a machine to be understood, but a living, breathing ecosystem of possibilities. Her colleague, Professor Heinrich Rothmann, represented the old guard's resistance. Probability waves, particles that exist in multiple states. Nonsense, he would scoff during heated debates at the Berlin Imperial Academy. Next, you'll be telling us that observation itself can change the nature of reality. Little did he know how prophetic those words would become. The scientific community was standing at the edge of a conceptual cliff. Their carefully constructed models of reality were about to be swept away by a tsunami of revolutionary understanding. The neat, orderly universe of classical physics was about to be replaced by something far more strange, far more wonderful. Quantum mechanics was not just a new scientific theory. It was a fundamental reimagining of reality itself. The challenge wasn't just scientific, it was philosophical, existential. If particles could exist in multiple states simultaneously, if observation could change the very nature of reality, what did that mean for human understanding? What did it mean for our conception of free will, of causality, of existence itself? Dr. Winters had a unique perspective that set her apart from her contemporaries. While others saw these emerging discoveries as technical problems to be solved, she saw them as windows into a deeper understanding of reality. Science is not about confirming what we already know, she would later write, but about being willing to completely destroy our existing understanding when new evidence demands it. The stage was set for a scientific revolution that would make previous paradigm shifts look like minor adjustments. The old guard of classical physics was about to be challenged by a new understanding of reality, so strange, so counterintuitive, that it would make everything that came before seem like a simplistic fairy tale. The universe was about to reveal its true mind-bending nature, and nothing would ever be the same again. The first true disruptive insight into the nature of reality came not from a grand laboratory or a prestigious scientific institution, but from a small, dimly lit research room in the basement of the University of Zurich. It was here that Dr. Elena Karoff first realized the world was far stranger than anyone had ever imagined. Her experiment was deceptively simple. A beam of light split into two paths, then reunited. Classical physics predicted a straightforward interference pattern, but what actually happened would begin to unravel the entire fabric of scientific understanding. When Elena first observed the results, she thought her equipment was malfunctioning. The light behaved in a way that defied all known physical laws. It was as if the light was simultaneously taking both paths, existing in multiple states at once, only resolving into a definitive path when observed. This was more than just an experimental anomaly. This was a fundamental challenge to the very nature of reality. The scientific world had long operated under the assumption of objective reality, that things exist independently of observation, with fixed properties waiting to be discovered. Elena's experiment suggested something far more radical, that reality itself might be a fluid, malleable construct, shaped by the very act of observation. Across the scientific community, whispers began to spread. Dr. Marcus Holloway dismissed these findings as the desperate fantasies of an over-imaginative mind. But others, more open-minded, recognized the profound implications. Dr. Alara Winters was particularly intrigued. During a private conversation with Elena, she articulated the deeper significance. "Imagine," she said, leaning forward with her characteristic intensity, "a universe where nothing is fixed until it is observed, where possibility itself is the fundamental state of existence." The implications were mind-bending. If light could exist in multiple states simultaneously, what did that mean for matter, for energy, for our understanding of reality itself? The experiment that would become known as the quantum path paradox was deceptively simple. A single photon was sent through a device that could split its path. Classical physics predicted the photon would take one path or the other, but the actual results were impossible to explain using existing scientific models. When the photon was not observed, it seemed to take both paths simultaneously. It was as if the photon existed in a state of pure potential, a cloud of probability that only collapsed into a definitive path when someone looked at it. This wasn't just strange. This was fundamentally impossible, according to everything science thought it knew about the universe. Elena's colleague, Dr. Friedrich Schneider, tried to replicate the experiment, convinced there must be some error, but each attempt produced the same impossible result. The photon behaved like a wave when unobserved, spreading out across multiple potential paths. The moment it was measured, it became a discrete particle, selecting a single path. It was as if reality itself was a choose-your-own-adventure story, with the act of observation writing the next chapter. The scientific community was deeply divided. Some saw this as the most exciting discovery in centuries. Others saw it as a threat to everything they understood about the universe. Dr. Marcus Holloway famously declared in a heated debate, "This is not science, this is madness." But Elena knew she had discovered something profound. "We are not measuring the universe," she would later write in her groundbreaking paper. "We are participating in its creation." The quantum path experiment revealed a fundamental truth. Reality is not a fixed stage, but a dynamic, interactive process. Particles are not things, but possibilities. Observation is not a passive act of discovery, but an active process of creation. This was more than a scientific discovery. This was a philosophical revolution. Imagine a universe where nothing is certain until it is observed, where possibilities exist in a state of pure potential, only resolving into definitive reality through the act of measurement, where the observer is not separate from the observed, but an integral part of the process of reality itself. The old mechanistic view of the universe was crumbling. In its place, a new understanding was emerging, fluid, dynamic, infinitely more complex and wonderful than anyone had ever imagined. Reality would never be the same again. The pioneers of quantum mechanics were not typical scientists. They were dreamers, rebels, and intellectual revolutionaries who dared to challenge the most fundamental assumptions about reality. Each of them brought a unique perspective that would ultimately shatter the existing scientific worldview. Dr. Elena Karoff stood at the forefront of this intellectual insurgency. Born to a family of Russian immigrants in Zurich, she had always been an outsider in the rigid world of early 20th century physics. Her wild copper-red hair and piercing green eyes matched her equally untamed intellectual spirit. Where other scientists saw boundaries, Elena saw possibilities. Across the scientific landscape, a handful of brilliant minds were converging, each approaching the quantum mystery from a different angle. In Berlin, Dr. Wilhelm Kreutzer was developing mathematical models that suggested particles could exist in multiple states simultaneously. In Paris, Dr. Antoinette Laurent was exploring the strange interactions between light and matter that defied classical understanding. But it was the collaboration between Elena Karov and Dr. Ilara Winters that would prove most revolutionary. Winters, with her background in both physics and philosophy, brought a unique perspective to their research. She saw quantum mechanics not just as a scientific theory, but as a profound reimagining of human understanding. "We are not just discovering the universe," she would often say. "We are negotiating its very nature." Their first joint research project was nothing short of audacious. They sought to understand how observation itself could fundamentally alter the behavior of subatomic particles. It was a concept so radical that most of their colleagues dismissed it as pure fantasy. Dr. Marcus Holloway, the most vocal critic of their work, would rage during academic conferences. "This is not science," he would thunder, his face turning an impressive shade of crimson. "This is mysticism dressed up in mathematical equations." But Elena and Ilara knew they were onto something profound. Their experiments revealed something extraordinary. Subatomic particles didn't just exist in a single state. They existed in a realm of pure potential, a probability cloud that only collapsed into a definitive state when observed. It was as if reality itself was a grand improvisation, constantly reshaping itself based on the act of perception. Wilhelm Kreutzer's mathematical models provided the theoretical framework. Antoinette Laurent's experimental work offered crucial empirical support. But it was Elena and Ilara who began to articulate the philosophical implications of their discoveries. In a small cafe in Zurich, over countless cups of strong black coffee, they would discuss the deeper meaning of their work. "We are discovering," Ilara would say, her eyes blazing with intellectual passion, "that the universe is not a machine. It's a living, breathing ecosystem of possibilities." Their research crossed traditional boundaries. They weren't just physicists. They were explorers of reality itself. Each of these pioneers brought something unique to the quantum revolution. Kreutzer's mathematical genius, Laurent's experimental precision, Winters's philosophical depth, Karov's audacious imagination. They were like a team of intellectual adventurers, each bringing a different tool to crack open the mysteries of the universe. The scientific establishment fought them at every turn. Grants were denied. Papers were rejected. Reputations were attacked. But they persisted. Their work challenged everything. The idea of objective reality, the notion of fixed time and space, the concept of causality itself. They were revealing a universe far more strange, far more wonderful than anyone had ever imagined. Dr. Elena Karov would later describe their journey in her memoirs. "We were not just scientists," she wrote. "We were midwives to a new understanding of reality. Each experiment, each mathematical model was a contraction, bringing a new way of seeing the world into existence." They were more than researchers. They were revolutionaries. The quantum pioneers understood something profound, that the act of discovery is itself a creative process, that science is not about confirming what we already know, but about being willing to completely destroy our existing understanding when new evidence demands it. As the old scientific order crumbled, a new understanding was emerging. Fluid, dynamic, infinitely more complex and wonderful than anyone had ever imagined. The universe was revealing its true nature, and nothing would ever be the same again. The first true breakthrough came on a rain-soaked evening in the winter of 1903. Dr. Elena Karov's laboratory was a sanctuary of controlled chaos, stacks of journals, intricate glass apparatus, and walls covered in mathematical equations that seemed to dance in the dim lamplight. What began as a routine experiment would become the moment that cracked open the universe's most profound secret. Elena had been studying the behavior of subatomic particles under extreme conditions. Her apparatus was deceptively simple: a sealed chamber, a precise light source, and a series of sophisticated measuring instruments that could detect the most minute interactions of matter and energy. The experiment seemed straightforward. A single photon would be sent through a specially designed apparatus that could split its path. Classical physics predicted a predictable outcome. The photon would take one path or another, simple, deterministic, controlled. Reality had other plans. When Elena first observed the results, she thought her equipment was malfunctioning. The photon didn't just take one path or another. It seemed to take both paths simultaneously. More incredibly, the act of observation itself appeared to collapse the photon's multiple potential states into a single, definitive path. It was as if the photon existed in a state of pure potential until the moment of measurement. Dr. Elara Winters, who was present during the experiment, described it later as a moment of cosmic revelation. "We weren't just measuring the particles," she wrote in her journal. "We were negotiating the very nature of reality." The implications were staggering. This wasn't just an obscure scientific curiosity. This was a fundamental challenge to everything humanity thought it knew about the nature of existence. Traditional scientific understanding assumed a universe of fixed states. Objects had definitive properties. Measurements revealed pre-existing conditions. But this experiment suggested something far more radical: that reality itself might be a fluid, malleable construct, shaped by the very act of observation. Dr. Wilhelm Kreutzer's mathematical models provided the theoretical framework to understand what was happening. The photon existed in what he called a probability wave, a cloud of potential states that only resolved into a definitive reality when observed. It was as if the universe was a grand improvisation, constantly reshaping itself based on perception. The scientific community was divided. Some saw this as the most exciting discovery in centuries. Others saw it as a fundamental threat to their understanding of reality. Dr. Marcus Holloway, the most vocal critic of these new ideas, denounced the findings in a heated academic conference. "This is not science," he thundered, his face turning an impressive shade of crimson. "This is mysticism, dressed up in mathematical equations." But Elena and her colleagues knew they had discovered something profound. They weren't just measuring the universe. They were participating in its creation. The breakthrough challenged multiple fundamental assumptions: causality, objectivity, the very nature of measurement itself. If observation could change the behavior of particles, what did that mean for our understanding of reality? Imagine a universe where nothing is certain until it is observed, where particles exist in a state of pure potential, only resolving into definitive reality through the act of measurement, where the observer is not separate from the observed, but an integral part of the process of reality itself. This was more than a scientific discovery. This was a philosophical revolution. Dr. Antoinette Laurent, another pioneer in the field, put it most eloquently. "We are not discovering the universe," she wrote. "We are in a constant dialogue with it. Each observation is a negotiation, each measurement a creative act." The implications stretched far beyond physics. If reality could be shaped by observation, what did that mean for human perception, for consciousness, for our understanding of free will? As news of the breakthrough spread, the scientific world found itself on the brink of a fundamental transformation. The neat, orderly universe of classical physics was crumbling. In its place, a new understanding was emerging, fluid, dynamic, infinitely more complex and wonderful than anyone had ever imagined. Reality would never be the same again. At the heart of quantum mechanics lay a concept so fundamental, yet so bizarre, that it would challenge the very foundations of human understanding. This was not merely a scientific theory. This was a radical reimagining of reality itself. Dr. Elena Karoff stood at the blackboard, her chalk dancing across the surface, creating a complex web of symbols and equations that seemed to breathe with their own mysterious life. "Fundamental concepts," she began, addressing the small group of researchers gathered in her private seminar room, "are not about complexity. They are about seeing the universe in its most elemental form." The core concept was deceptively simple, yet infinitely profound. The wave function, represented by the Greek letter psi, it was more than just a mathematical construct. It was a description of pure potential, a mathematical representation of every possible state a quantum system could occupy. Imagine a universe where nothing is fixed, where particles exist not as definitive objects, but as clouds of probability, where every potential state exists simultaneously until the moment of observation. This was the essence of the wave function. Dr. Alara Winters explained it most poetically during one of their late-night discussions. "The wave function," she would say, her eyes gleaming with intellectual passion, "is not a description of what is. It's a description of what could be." To understand this concept, one had to abandon everything they thought they knew about reality. In the classical world, an object has definitive properties. A ball is red. A car is moving at 60 kilometers per hour. A particle is at a specific location. But in the quantum realm, nothing is so certain. A particle exists in multiple states simultaneously, a concept so counterintuitive that it seemed to border on madness. Dr. Wilhelm Kreutzer had developed the mathematical framework that gave this concept its rigor. His equations showed how a particle could exist in multiple states at once, with each state having a specific probability of being observed. It was like a cosmic lottery, where every ticket is a potential reality. During a groundbreaking lecture at the Berlin Imperial Academy, Kreutzer demonstrated this using a simple thought experiment. Imagine a box containing a cat. Quantum mechanics suggests that until the box is opened, the cat is simultaneously alive and dead, existing in both states at once. It's only when someone opens the box that reality collapses into a single state. This was the famous Schrödinger's cat thought experiment, which would become one of the most discussed concepts in quantum mechanics. The implications were mind-bending. Reality was not a fixed stage, but a dynamic, interactive process. Particles were not things, but possibilities. Observation was not a passive act of discovery, but an active process of creation. Dr. Antoinette Laurent took this concept even further in her research. She demonstrated that the very act of measurement doesn't just reveal a pre-existing state, it actually creates that state. Before measurement, a particle exists in multiple potential states simultaneously. The measurement itself causes the wave function to collapse into a single, definitive reality. It was as if the universe was a grand improvisational performance, with reality constantly being negotiated through the act of observation. This flew in the face of everything classical physics believed. In the old model, the universe was a massive, predictable machine. Every particle had a definitive position and momentum. Cause followed effect in a neat, linear progression. But quantum mechanics revealed a universe far more strange and wonderful. We are not discovering the universe, Elena would often say. We are participating in its creation. The core concept was both terrifyingly simple and profoundly complex. Probability was not just a mathematical tool, but the fundamental fabric of reality itself. Every particle existed in a state of pure potential, a cloud of possibilities that only resolved into a definitive state through observation. Imagine a universe where nothing is certain, where every potential outcome exists simultaneously, where reality is not a fixed script, but a constant negotiation between possibility and actuality. This was more than a scientific theory. This was a fundamental reimagining of existence itself. As Dr. Marcus Holloway continued to rage against these ideas, the younger generation of scientists saw something magnificent. They were not just studying the universe, they were uncovering its most fundamental nature, a nature far more complex, far more beautiful than anyone had ever imagined. Reality would never be the same again. The philosophical implications of quantum mechanics ran deeper than any scientific discovery in human history. This was not merely a new understanding of physics. This was a fundamental challenge to human perception, to our understanding of consciousness, to the very nature of reality itself. Dr. Ilara Winters understood this better than anyone. On a crisp autumn evening, in her private study overlooking the misty streets of Zurich, she began to unravel the profound philosophical dimensions of their discoveries. "We are not just describing the universe," she wrote in her personal journal, the pages illuminated by a soft amber lamp. "We are discovering the fundamental language of existence." Quantum mechanics revealed a universe that was fundamentally different from everything humanity had believed. In the classical world, reality was fixed, objective, predictable. You could measure something, and that measurement would reveal a pre-existing state. Cause followed effect in a neat, linear progression. But quantum mechanics suggested something far more radical. Reality was not a fixed stage. It was a dynamic, interactive process. Particles were not things, but possibilities. Observation was not a passive act of discovery, but an active process of creation. The great philosophical questions that had haunted humanity for millennia suddenly took on new meaning. What is consciousness? What is the nature of perception? Are we observers of reality or participants in its creation? Dr. Wilhelm Kreutzer approached these questions from a mathematical perspective. His equations suggested that consciousness itself might be more than just a biological phenomenon. It was potentially a fundamental aspect of reality, a cosmic process of observation and creation. During a heated debate at the Berlin Imperial Academy, Kreutzer proposed a revolutionary idea. Consciousness, he argued, might not be something that happens in the brain. It might be a fundamental property of the universe itself, a process of continuous creation and observation. The room fell silent. Dr. Antoinette Laurent took these ideas even further. Her research suggested that the act of observation was not just a physical interaction, but a deeply participatory process. We are not separate from the universe, she would argue. We are the universe experiencing itself. It was a profound reimagining of human existence. The Shakespeare quote that Dr. Elena Karoff often cited took on new meaning. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Quantum mechanics was proving this in ways no one could have imagined. Consider the philosophical implications. If observation creates reality, what does that mean for free will, for consciousness, for the very nature of existence? The old materialistic view of the universe, a massive, deterministic machine operating according to fixed laws, was crumbling. In its place, a new understanding was emerging. The universe was not a machine. It was a living, breathing ecosystem of possibilities. Dr. Marcus Holloway continued to rail against these ideas. "This is mysticism," he would thunder during academic conferences. But the younger generation of scientists saw something magnificent. They were uncovering a fundamental truth about reality, a truth far more complex and wonderful than anyone had ever imagined. The boundaries between science and philosophy were dissolving. Quantum mechanics was revealing that the universe was not just stranger than we imagine, but stranger than we could imagine. Meditation traditions had spoken for millennia about the interconnectedness of all things. Now, quantum mechanics was providing a scientific framework for understanding this interconnection. Particles that had once interacted could remain mysteriously connected across vast distances, a phenomenon Einstein had dismissively called spooky action at a distance. But what if this was not spooky, but fundamental? What if connection was the basic state of the universe, and separation was the illusion? Dr. Elena Karoff saw this as the most profound discovery of their research. "We are not isolated beings," she would say. "We are expressions of a fundamental, interconnected reality. Our separation is an illusion created by limited perception." This was more than a scientific theory. This was a spiritual revolution. The universe was revealing itself as a vast, interconnected web of possibilities, where every observation was a creative act, where consciousness was not something that happened in our brains, but a fundamental process of reality itself. Reality would never be the same again. Technical understanding requires more than just abstract concepts. It demands a foundation that can transform the incomprehensible into something tangible, something that bridges the gap between mathematical abstraction and human intuition. Dr. Elena Karoff understood this better than anyone. Her laboratory was a sanctuary of precision, where complex ideas were transformed into concrete experiments. On the walls, intricate diagrams danced alongside mathematical equations, each one a carefully crafted window into the fundamental nature of reality. The first layer of technical explanation began with the most basic building blocks of quantum understanding, the fundamental principles that govern the behavior of subatomic particles. Consider light, that seemingly simple phenomenon that had puzzled scientists for centuries. Classical physics had long treated light as either a wave or a particle, a binary choice that seemed straightforward. But quantum mechanics revealed a far more complex reality. Light, it turned out, was neither purely a wave nor purely a particle. It existed in a state of quantum superposition, simultaneously displaying wave-like and particle-like properties. This was not a limitation of measurement, but a fundamental characteristic of reality itself. Dr. Antoinette Laurent's experiments provided the most compelling evidence. Using a sophisticated apparatus that could detect the most minute interactions of light, she demonstrated how a single photon could pass through multiple slits simultaneously, creating an interference pattern that defied classical understanding. Imagine, she would explain to her students, a single particle that can exist in multiple places at once, not because we can't see it, but because that is its fundamental nature. The mathematical language that described this behavior was equally fascinating. Wave functions, represented by the Greek letter psi, became the mathematical description of quantum possibility. These were not simple equations, but complex mathematical representations of pure potential. Dr. Wilhelm Kreutzer had developed the most sophisticated mathematical models to describe this quantum behavior. His equations showed how a particle could exist in multiple states simultaneously, with each state having a specific probability of being observed. It's like a cosmic lottery, Kreutzer would explain, his eyes sparkling with intellectual excitement. Every possible outcome exists simultaneously, with different probabilities of being realized. The technical depth was staggering. Quantum mechanics introduced entirely new mathematical concepts: probability waves, quantum superposition, wave-particle duality. Each concept was a hammer blow to classical understanding, revealing a universe far more strange and wonderful than anyone had imagined. Take the concept of quantum entanglement, a phenomenon so bizarre that Einstein called it spooky action at a distance. Two particles could become mysteriously linked, such that measuring the state of one instantly affected the other, regardless of the distance between them. Dr. Elena Karov's experiments demonstrated this most dramatically. Two entangled particles, separated by meters, would instantaneously reflect each other's quantum states. It was as if they were connected by an invisible thread that transcended space and time. The technical language was precise, but the implications were profound. These were not just mathematical curiosities. These were fundamental revelations about the nature of reality itself. Quantum uncertainty became a key principle. The famous Heisenberg uncertainty principle showed that certain pairs of physical properties, like position and momentum, could not be precisely determined simultaneously. The more precisely you measured one property, the less precisely you could know the other. This was not a limitation of measurement technology. This was a fundamental characteristic of reality itself. Dr. Ilara Winters saw the deeper significance. We are not measuring a pre-existing reality, she would explain. We are participating in the creation of reality through the act of observation. The technical foundations revealed a universe that was fundamentally probabilistic, not random, but filled with intricate possibilities. Each measurement was not a revelation of a pre-existing state, but a creative act that collapsed multiple potential realities into a single observed outcome. Imagine a universe where nothing is fixed, where particles exist as clouds of probability, where observation itself is a creative process that shapes reality. This was more than a scientific theory. This was a fundamental reimagining of existence. As Dr. Marcus Holloway continued to rage against these ideas, the younger generation of scientists saw something magnificent. They were not just studying the universe. They were uncovering its most fundamental nature, a nature far more complex, far more beautiful than anyone had ever imagined. Reality would never be the same again. The most counterintuitive aspects of quantum mechanics lurked in the shadows of human perception, challenging everything we thought we knew about the nature of reality. Dr. Elena Karoff stood at the edge of human understanding, peering into an abyss of scientific possibility that seemed to defy logic itself. The quantum world was not just strange, it was fundamentally alien to human intuition. Consider the most mind-bending concept: quantum superposition. Imagine a particle that doesn't exist in a single state, but in multiple states simultaneously. It's not that we don't know its exact state. It literally exists in all possible states at once, only resolving into a single state when observed. Dr. Antoinette Laurent loved to illustrate this with a thought experiment. Imagine a coin, she would say to her students, that is simultaneously heads and tails until the moment you look at it. Not just uncertain, but actually existing in both states at the same time. The human mind recoils from such a concept. Our entire evolutionary history has prepared us to understand a world of fixed states, of definitive realities. We see a tree. We know it's a tree. We touch a rock. We know it's a rock. But quantum mechanics suggested something far more radical, that reality is fundamentally fluid, fundamentally uncertain. Dr. Wilhelm Kreutzer's mathematical models revealed the depth of this uncertainty. Particles didn't have fixed properties. They existed as probability waves, clouds of potential that only collapsed into a definitive state through the act of observation. It's as if reality is a cosmic improvisation, Ilara Winters would often say, a constant negotiation between possibility and actuality. The most shocking experiments challenged the very notion of objective reality. In the famous double-slit experiment, a single particle would somehow pass through two separate slits simultaneously, creating an interference pattern that suggested the particle existed in multiple places at once. It was as if the particle was playing a cosmic game of hide-and-seek, existing everywhere and nowhere until someone looked. Even more bizarre was the concept of quantum entanglement. Two particles could become mysteriously linked, such that measuring the state of one instantly affected the other, regardless of the distance between them. Einstein called this spooky action at a distance, a phenomenon that seemed to violate everything we understood about cause and effect. Imagine two coins separated by thousands of miles. Flip one, and the other instantly flips as well. Not through any known communication, but through some fundamental connection that transcended space and time. The counterintuitive nature went deeper. The very act of observation changed the behavior of quantum systems. It wasn't that our measurement was imperfect. The measurement itself was a creative act that collapsed multiple potential realities into a single observed outcome. Dr. Marcus Holloway would rage against these ideas. "Nonsense," he would thunder during academic conferences. "This is mysticism, not science." But the younger generation saw something profound. They were uncovering a fundamental truth about reality, a truth far more complex and wonderful than anyone had ever imagined. The famous Schrodinger's cat thought experiment captured this perfectly. Imagine a cat in a sealed box with a device that may or may not kill the cat based on a quantum event. According to quantum mechanics, until the box is opened, the cat is simultaneously alive and dead, existing in both states at once. It sounds like madness, but this was the fundamental nature of quantum reality. Dr. Elena Karoff understood the philosophical depth of these discoveries. "We are not separate from the universe," she would say. "We are the universe experiencing itself. Our observation is not passive. It is a creative act that shapes reality itself." The implications were staggering. Free will, consciousness, the nature of reality itself, all were called into question. If observation creates reality, what does that mean for human perception? Are we passive observers or active participants in the creation of existence? Traditional scientific understanding assumed a universe of fixed states. Objects had definitive properties. Measurements revealed pre-existing conditions. But quantum mechanics suggested something far more radical, that reality itself might be a fluid, malleable construct shaped by the very act of observation. As Dr. Ilara Winters wrote in her groundbreaking journal, "We are not discovering the universe. We are in a constant dialogue with it. Each observation is a negotiation, each measurement a creative act." The universe was revealing itself as a vast, interconnected web of possibilities, where every observation was a creative act, where consciousness was not something that happened in our brains, but a fundamental process of reality itself. Reality would never be the same again. Mathematics was not just a language of description in quantum mechanics. It was the fundamental architecture of reality itself. Dr. Wilhelm Kreutzer's office was a sacred space of mathematical revelation. Massive chalkboards covered every wall, filled with intricate equations that seemed to breathe with their own mysterious life. Each symbol was not merely a mathematical notation, but a gateway to understanding the fundamental nature of existence. The mathematical foundation of quantum mechanics began with seemingly simple equations that concealed profound complexity. The wave function, represented by the Greek letter psi, was more than just a mathematical construct. It was a comprehensive description of a quantum system's entire possible state of existence. Imagine an equation that could describe not just what is, but every possible thing that could be. An equation that represented pure potential. The Schrödinger equation emerged as the fundamental mathematical language of quantum mechanics. At first glance, it appeared deceptively simple. IH partial derivative of psi with respect to t equals HP psi. But this seemingly straightforward notation contained the keys to understanding the most profound mysteries of the universe. Dr. Elena Karoff would often explain it to her students with a mixture of scientific precision and philosophical wonder. "This equation," she would say, her eyes blazing with intellectual passion, "is not just a description. It's a cosmic negotiation between possibility and reality." The mathematics revealed layers of complexity that defied classical understanding. Probability amplitudes replaced definitive measurements. Complex numbers became the fundamental language of quantum description. Where classical physics dealt in absolutes, quantum mathematics dealt in probabilities, in potentials, in the space between what is and what could be. Dr. Antoinette Laurent specialized in translating these abstract mathematical concepts into tangible understanding. Think of it like a cosmic lottery, she would explain. Every possible outcome exists simultaneously, with different probabilities of being realized. The mathematical foundations introduced entirely new conceptual frameworks. Quantum superposition meant that a system could exist in multiple states simultaneously. The uncertainty principle, mathematically expressed as delta x delta po p greater than or equal to h bar divided by 2, showed that certain pairs of physical properties could not be precisely determined simultaneously. This was not a limitation of measurement. This was a fundamental characteristic of reality itself. Dr. Alara Winters saw the deeper philosophical implications. Mathematics is not just describing the universe, she would argue during late-night discussions. It is the fundamental language through which the universe expresses itself. The complex numbers that populated quantum equations were particularly fascinating. Unlike the simple real numbers of classical mathematics, these complex numbers suggested multiple dimensions of possibility. A number that included both real and imaginary components became a metaphor for the quantum understanding of reality. Imagine an equation where numbers are not just quantities, but gateways to multiple potential realities. The mathematical models developed by Kreutzer and his colleagues showed how particles could be described as probability waves. Each equation was a map of possibility, showing not where something is, but where it could be. The probability of finding a particle in a particular location was represented by the square of the wave function's magnitude. Dr. Marcus Holloway continued to rail against these mathematical abstractions. "This is numerology, not science," he would thunder during academic conferences. But the younger generation of scientists saw something magnificent. They were uncovering the mathematical language of reality itself. Quantum field theory took this even further. It suggested that particles were not fundamental entities, but excitations in underlying quantum fields that permeated all of space. The mathematics revealed a universe far more interconnected than anyone had imagined. The mathematical foundations were revealing a universe that was fundamentally probabilistic, not random, but filled with intricate possibilities. Each equation was a window into a reality far more complex and wonderful than classical physics had ever suggested. Quantum mechanics transformed mathematics from a tool of description to a method of exploration. Each equation was a journey into the unknown, a probe into the fundamental nature of existence. Dr. Elena Karoff would often quote the mathematician Johannes Kepler, "Geometry is one and eternal, a reflection from the mind of God." Now, quantum mechanics was suggesting that mathematics was not just a reflection, but the very language of creation itself. As the chalkboards in Kreutzer's office filled with ever more complex equations, humanity stood on the brink of a profound revelation. The universe was not a machine to be understood, but a living, breathing mathematical symphony waiting to be heard. Reality would never be the same again. The practical applications of quantum mechanics were about to transform human civilization in ways no one could have imagined. Dr. Elena Karoff's laboratory was more than a scientific workspace. It was a crucible of potential where abstract theories met tangible reality. Her team understood something profound. Quantum mechanics was not just a theoretical exercise. It was a toolkit for reimagining human technology. Consider the most immediate applications. Electronics had been operating on classical principles for decades, but quantum mechanics revealed entirely new possibilities for understanding and manipulating matter at its most fundamental level. Semiconductors, the backbone of modern computing, were the first major breakthrough. Traditional electronics relied on understanding how electrons moved through materials. Quantum mechanics provided a fundamentally different approach, allowing scientists to precisely manipulate electron behavior at the atomic scale. Dr. Antoinette Laurent was particularly excited about quantum computing. "Imagine a computer," she would explain to her increasingly fascinated students, "that doesn't just calculate sequentially, but can explore multiple possibilities simultaneously." Traditional computers used binary logic, zeros and ones. Quantum computers could exist in multiple states at once, exploring countless potential solutions simultaneously. It was like having millions of computers working in parallel within a single machine. Telecommunications would be revolutionized by quantum encryption. Dr. Wilhelm Kreutzer's research showed how quantum entanglement could create unbreakable communication channels. Two entangled particles could transmit information instantaneously, regardless of distance, with absolute security. Medical imaging represented another frontier. Quantum mechanics allowed for unprecedented precision in understanding molecular interactions. Imagine medical scanners that could detect diseases at the cellular level, long before traditional methods could identify them. Energy production stood on the brink of a fundamental transformation. Quantum tunneling, a phenomenon where particles could pass through seemingly impossible barriers, suggested entirely new approaches to solar energy, nuclear fusion, and quantum battery technologies. Dr. Ilara Winters saw the broader implications. "We're not just developing new technologies," she would argue. "We're learning the fundamental language of creation itself." Materials science was perhaps the most immediately transformative field. Quantum mechanics allowed scientists to design materials with precisely engineered properties at the atomic level. Superconductors that worked at room temperature, metamaterials with impossible characteristics, quantum-engineered surfaces that could repel water, conduct electricity in entirely new ways, or self-repair. The military and aerospace industries were particularly interested. Quantum sensors could detect gravitational waves with unprecedented precision. Navigation systems could become infinitely more accurate. Stealth technologies could be revolutionized by understanding quantum interactions. But the most profound applications were still unimaginable. Dr. Elena Karoff understood that they were not just developing technologies. They were learning to speak the fundamental language of reality itself. Each breakthrough, she would say, is not just a technological advancement. It's a new word in the cosmic conversation. Quantum biology was emerging as a radical new field. Living systems, it turned out, might be using quantum mechanisms in ways no one had previously understood. Photosynthesis, bird navigation, even human consciousness might involve quantum-level interactions. The pharmaceutical industry stood to be completely transformed. By understanding molecular interactions at the quantum level, researchers could design drugs with unprecedented precision. Targeted therapies that could attack specific cellular mechanisms became possible. Dr. Marcus Holloway, who had long been a skeptic, was forced to acknowledge the practical potential. These are not just theoretical curiosities, he grudgingly admitted during a conference. These are fundamental technologies that will reshape human civilization. Quantum artificial intelligence represented perhaps the most mind-bending frontier. Machines that could not just calculate but explore multiple potential realities simultaneously. Intelligences that could process information in ways that transcended classical computational limits. The practical applications were limited only by human imagination. And human imagination, as quantum mechanics was revealing, was far more expansive than anyone had previously believed. Dr. Alara Winters captured the essence of this transformation in her final lecture before retiring. "We are not just developing technologies," she told a packed auditorium. "We are learning to negotiate with reality itself. Each quantum breakthrough is a conversation with the fundamental nature of existence. Reality would never be the same again. Experimental evidence was the crucible that would transform quantum mechanics from a radical theory to a fundamental understanding of reality." The small research facility, nestled in the misty highlands of New Caledonia, looked more like an artist's studio than a cutting-edge scientific laboratory. Delicate glass apparatuses, intricate measuring instruments, and walls covered with complex diagrams created an atmosphere of controlled chaos. Dr. Elena Karoff stood at the center of this scientific sanctuary, her eyes burning with an intensity that matched the revolutionary nature of her research. Experimental proof was not just about validation, it was about revealing the fundamental nature of reality itself. The double-slit experiment became the cornerstone of quantum mechanical understanding. On the surface, it seemed simple. A beam of particles, electrons or photons, would be fired through two narrow slits towards a detection screen. Classical physics predicted a straightforward pattern. Reality had other plans. When individual particles were fired, one at a time, something extraordinary happened. Instead of creating two distinct bands, the particles created an interference pattern, as if each particle was somehow passing through both slits simultaneously. It was as if each particle existed in multiple states, only resolving into a definitive path when observed. Dr. Antoinette Laurent's meticulous documentation became legendary. "We are not measuring a pre-existing reality," she would write in her research notes. "We are participating in the creation of reality through the act of observation." The quantum entanglement experiments pushed experimental understanding even further. Two particles would be created in such a way that their quantum states were mysteriously linked. Measure the state of one particle, and the state of the other would instantaneously change, regardless of the distance between them. Einstein had called this spooky action at a distance, convinced it proved the incompleteness of quantum theory. But repeated experiments proved it was a fundamental characteristic of reality. Dr. Wilhelm Kreutzer's mathematical models provided the theoretical framework, but it was the experiments that truly revealed the bizarre nature of quantum reality. Particles could exist in multiple states simultaneously. Observation itself seemed to collapse these multiple possibilities into a single reality. The Stern-Gerlach experiment provided another crucial piece of experimental evidence. Atoms passed through a magnetic field would be deflected in discrete, quantized ways, not continuously as classical physics predicted, but in specific, precise increments. Each experiment was a window into a reality far more complex than anyone had imagined. Quantum tunneling experiments revealed perhaps the most mind-bending evidence. Particles could pass through seemingly impossible barriers, as if the very laws of classical physics were merely suggestions. It was like watching a baseball spontaneously pass through a solid wall, defying every known principle of classical mechanics. Dr. Alara Winters saw the deeper significance. These are not just experimental results, she would argue during late-night discussions. These are conversations with the fundamental nature of reality. The experimental evidence challenged every fundamental assumption about the nature of existence. Particles were not solid objects, but probability waves. Time and space were not fixed stages, but fluid, interconnected dimensions. Dr. Marcus Holloway continued to rail against these discoveries. "This is madness," he would thunder during academic conferences. But the experimental evidence was overwhelming. Reality was far stranger than anyone had imagined. Quantum interference experiments showed that particles could interfere with themselves, as if they existed in multiple places simultaneously. The famous delayed choice quantum eraser experiment suggested that measurement could retroactively change the behavior of particles, challenging even our most basic understanding of cause and effect. Each experiment was a hammer blow to classical understanding. Particles were not things, but possibilities. Observation was not a passive act of discovery, but an active process of creation. The experimental evidence revealed a universe that was fundamentally probabilistic, not random, but filled with intricate possibilities. A cosmic dance of potential where reality was constantly negotiated through the act of observation. Dr. Elena Karoff understood the profound implications. "We are not discovering the universe," she would say. "We are in a constant dialogue with it. Each experiment is a question. Each observation is an answer." As the experimental evidence accumulated, humanity stood on the brink of a profound revelation. The universe was not a machine to be understood, but a living, breathing ecosystem of possibilities waiting to be explored. Reality would never be the same again. Probability became the language of fundamental reality, transforming our understanding from certainty to a complex dance of possibilities. In the small, dimly lit seminar room of the New Caledonia Research Institute, Dr. Elena Karoff stood before a group of wide-eyed students, ready to unravel the most counterintuitive concept in scientific history. Probability was not just a mathematical tool, it was the fundamental fabric of existence itself. "Imagine," she began, her voice low and intense, "a universe where nothing is fixed, where every possible outcome exists simultaneously, waiting to be realized." Classical physics had treated probability as a measure of our ignorance. If you couldn't precisely measure something, it was a limitation of measurement. Quantum mechanics revealed something far more radical. Probability was the fundamental state of reality. Dr. Antoinette Laurent had a favorite demonstration. She would take a simple coin and challenge her students to predict its outcome. In classical physics, you might calculate probabilities based on incomplete information. In quantum mechanics, probability was not just about incomplete knowledge. It was the fundamental nature of reality itself. Consider the wave function, that mathematical description of quantum possibilities. It wasn't just a prediction, it was a comprehensive map of every potential state a quantum system could occupy. The square of the wave function's magnitude represented the probability of finding a particle in a particular location. Dr. Wilhelm Kreutzer's mathematical models revealed the depth of this probabilistic understanding. Particles didn't have fixed properties. They existed as probability waves, clouds of potential that only collapsed into a definitive state through the act of observation. The famous Schrödinger's cat thought experiment captured this perfectly. A cat in a sealed box with a device that may or may not kill it based on a quantum event exists in a state of multiple possibilities. Until observed, the cat is simultaneously alive and dead, not just unknown, but literally existing in multiple states at once. This was not a limitation of measurement. This was a fundamental characteristic of reality. Quantum uncertainty became a key principle. The Heisenberg uncertainty principle showed that certain pairs of physical properties, like position and momentum, could not be precisely determined simultaneously. The more precisely you measured one property, the less precisely you could know the other. Dr. Ilara Winters saw the profound philosophical implications. We are not passive observers, she would argue during late-night discussions. We are active participants in the creation of reality. Our observation is not a revelation of a pre-existing state, but a creative act that collapses multiple possibilities into a single outcome. Probability in quantum mechanics was fundamentally different from classical probability. In classical physics, probability represented our incomplete understanding. In quantum mechanics, probability was the fundamental state of existence. Imagine rolling a classical die. You might not know which number will come up, but the die has a fixed state before rolling. In the quantum world, it's as if the die exists in all possible states simultaneously, only resolving into a specific number when observed. The double-slit experiment provided the most compelling evidence. Individual particles, electrons or photons, would create an interference pattern when fired, one at a time, as if each particle was simultaneously taking multiple paths. It was not that we couldn't track the particle. The particle literally existed in multiple states at once. Dr. Marcus Holloway continued to rail against these probabilistic interpretations. "This is nonsense," he would thunder during academic conferences. "The universe is not a game of chance." But the younger generation of scientists saw something magnificent. They were uncovering a fundamental truth about reality, a truth far more complex and wonderful than anyone had ever imagined. Quantum probability suggested that reality is not a fixed stage, but a dynamic, interactive process. Particles are not things, but possibilities. Observation is not a passive act of discovery, but an active process of creation. Dr. Elena Karoff would often quote the mathematician Johannes Kepler, "Geometry is one and eternal, a reflection from the mind of God." Now, quantum mechanics was suggesting that probability was the very language of creation itself. The practical implications were profound. Quantum computing, quantum encryption, quantum biology, all relied on this fundamental probabilistic nature of reality. Technologies that could explore multiple possibilities simultaneously were becoming possible. As the chalkboards filled with complex probability distributions, humanity stood on the brink of a profound revelation. The universe was not a machine to be understood, but a living, breathing ecosystem of possibilities. Reality would never be the same again. The limitations of measurement in quantum mechanics revealed something far more profound than a simple technical challenge. They exposed the fundamental nature of reality itself. Dr. Elena Karov's laboratory had become a sanctuary of scientific exploration, where the very act of observation was treated as a creative process. The walls were covered with intricate diagrams, each one a testament to the complex dance between observer and observed. Measurement in the quantum world was not a passive act of discovery. It was an active intervention that fundamentally altered the nature of reality. The most striking demonstration came from the infamous observer effect. Unlike classical physics, where measurement was presumed to be a neutral act of discovery, quantum mechanics suggested something far more radical. The very act of observations changes the system being observed. Dr. Antoinette Laurent had perfected a series of experiments that demonstrated this principle with stunning clarity. Imagine trying to measure the position of an electron. The very act of attempting to observe its location would fundamentally change its momentum. The more precisely you measured its position, the more uncertain its momentum became. It was as if reality was a delicate ecosystem constantly reshaped by the act of perception. Dr. Wilhelm Kreutzer's mathematical models provided the theoretical framework. The Heisenberg uncertainty principle wasn't just a limitation of measurement technology, it was a fundamental characteristic of reality itself. Certain pairs of physical properties, position and momentum, energy and time, could not be precisely determined simultaneously. We are not measuring a pre-existing reality, Dr. Ilara Winters would argue during her lectures. We are participating in the creation of reality through the act of observation. The quantum measurement problem became a fundamental philosophical challenge. In classical physics, measurement was straightforward. You observed a system, and that observation revealed its pre-existing state. Quantum mechanics suggested something far more radical, that the act of measurement itself creates the reality being measured. The famous Schrödinger's cat thought experiment captured this perfectly. A cat in a sealed box with a device triggered by a quantum event that may or may not kill it exists in a state of multiple possibilities. Until the box is opened and the cat is observed, it exists simultaneously in multiple states, both alive and dead. This was not a limitation of human perception. This was a fundamental characteristic of reality itself. Practical measurement challenges emerged in multiple scientific fields. In quantum computing, maintaining the delicate quantum states of particles became a monumental challenge. The very act of attempting to read or measure these states would cause them to collapse, destroying the quantum information. Dr. Marcus Holloway continued to rail against these interpretations. "This is mysticism," he would thunder during academic conferences. "Science is about objective measurement." But the experimental evidence was overwhelming. Reality was far more fluid, far more interactive than anyone had imagined. Quantum encryption provided a practical demonstration of these measurement limitations. By leveraging the fundamental uncertainty of quantum systems, completely secure communication became possible. Any attempt to measure the quantum state would fundamentally alter that state, making interception impossible. The measurement challenge extended beyond physics. Quantum biology suggested that living systems might be using quantum mechanisms in ways we were only beginning to understand. Photosynthesis, bird navigation, even human consciousness might involve quantum-level interactions that were fundamentally altered by observation. Dr. Elena Karoff saw the broader implications. "We are not separate from the universe," she would say. "We are participants in its continuous creation. Each observation is a negotiation, each measurement a creative act." Imagine a universe where observation is not a passive act of discovery, but an active process of creation, where reality is not a fixed stage, but a dynamic, interactive ecosystem of possibilities. The practical and philosophical implications were profound. If observation creates reality, what does that mean for human perception, for consciousness, for our understanding of free will? As measurement technologies became more sophisticated, the quantum measurement challenge became both a technical problem and a philosophical frontier. Each new experiment revealed layers of complexity that defied classical understanding. Dr. Ilara Winters captured the essence of this transformation in her final lecture. "We are learning to speak the fundamental language of reality," she told a packed auditorium. "Each measurement is a question, each observation is an answer." Reality would never be the same again. Technological transformation was no longer a distant promise. Quantum mechanics was rewriting the very fabric of human innovation, creating possibilities that once belonged solely to the realm of science fiction. The research facility in New Caledonia had become more than a scientific laboratory. It was a forge of future technologies, where the boundaries between imagination and reality blurred into something extraordinary. Dr. Elena Karoff stood before a prototype that would revolutionize computing, a quantum computer that could perform calculations impossible for classical machines, not by being faster, but by existing in multiple states simultaneously. It was a technological leap that made traditional computers look like ancient abacuses. Dr. Antoinette Laurent's work in quantum communication had already produced breakthroughs that would reshape global communication. Quantum encryption created communication channels that were theoretically unbreakable. Information could be transmitted with absolute security, protected by the fundamental uncertainty of quantum systems. "We are not just developing technologies," Dr. Ilara Winters would argue during strategy meetings. "We are learning to speak the fundamental language of the universe." The medical field stood on the brink of a revolution. Quantum sensing technologies could detect diseases at the cellular level, long before traditional diagnostics. Imagine medical scanners that could map the quantum interactions within living cells, revealing the earliest signs of disease with unprecedented precision. Dr. Wilhelm Kreutzer's research into quantum biology revealed even more mind-bending possibilities. Living systems might be using quantum mechanisms in ways no one had previously understood. Photosynthesis, bird navigation, even human consciousness might involve quantum-level interactions that could now be precisely mapped and potentially manipulated. Energy production was being completely reimagined. Quantum tunneling suggested entirely new approaches to solar energy, nuclear fusion, and battery technologies. Materials could be engineered at the atomic level, creating surfaces that could repel water, conduct electricity in entirely new ways, or self-repair. The aerospace and military industries were particularly fascinated. Quantum sensors could detect gravitational waves with impossible precision. Navigation systems could become infinitely more accurate. Stealth technologies could be revolutionized by understanding quantum interactions. Artificial intelligence was about to undergo a fundamental transformation. Quantum computing suggested the possibility of machines that could explore multiple potential realities simultaneously, intelligences that could process information in ways that transcended classical computational limits. Dr. Marcus Holloway, who had long been a skeptic, was forced to acknowledge the potential. These are not just theoretical curiosities, he grudgingly admitted during a conference. These are technologies that will reshape human civilization. The most profound technological potential lay in quantum computing. Traditional computers used binary logic, zeros and ones. Quantum computers could exist in multiple states simultaneously, exploring countless potential solutions in parallel. It was like having millions of computers working together within a single machine. Quantum materials were being developed that defied classical understanding. Superconductors that worked at room temperature, metamaterials with impossible characteristics, surfaces that could change their properties on demand, adapting to environmental conditions in real time. Quantum cryptography promised absolute security, communication channels that were fundamentally protected by the laws of quantum mechanics. Any attempt to intercept the communication would fundamentally alter the quantum state, making interception impossible. The pharmaceutical industry stood to be completely transformed. By understanding molecular interactions at the quantum level, researchers could design drugs with unprecedented precision. Targeted therapies that could attack specific cellular mechanisms became possible. Dr. Elena Karov saw the broader implications. "We are not just developing technologies," she would say. "We are learning to negotiate with reality itself. Each quantum breakthrough is a conversation with the fundamental nature of existence." The practical applications seemed limited only by human imagination. And human imagination, as quantum mechanics was revealing, was far more expansive than anyone had previously believed. Quantum technologies were revealing a fundamental truth. Reality is not a fixed stage, but a dynamic, interactive process. Technologies that could explore multiple possibilities simultaneously were becoming possible. Dr. Alara Winters captured the essence of this transformation in her final lecture. "We are not just creating new technologies," she told a packed auditorium. "We are learning to speak the fundamental language of the universe." As prototypes filled the research facility, humanity stood on the brink of a technological revolution that would make previous scientific advances look like mere preludes. Reality would never be the same again. Metaphors became the bridge between the incomprehensible quantum world and human understanding, transforming abstract scientific concepts into narratives that could penetrate the human imagination. Dr. Elena Karov understood that scientific revolution was as much about storytelling as it was about mathematical precision. Her office walls were covered not just with equations, but with intricate diagrams and metaphorical illustrations that attempted to capture the essence of quantum reality. "Imagine the universe as a massive improvisation," she would begin her lectures, her eyes sparkling with intellectual passion. "Not a scripted performance, but a living, breathing ecosystem of possibilities. The quantum world defied traditional explanation. How do you describe a reality where particles exist in multiple states simultaneously, where observation itself creates reality, where the fundamental nature of existence is more like a dance of possibilities than a fixed stage? Dr. Antoinette Laurent had developed a particularly compelling metaphor. Think of reality as a cosmic choose-your-own-adventure book, she would tell her students. Every page exists simultaneously. The act of reading, of observing, determines which narrative becomes real. The double-slit experiment became a perfect metaphorical landscape. Imagine a particle as a traveler with an infinite number of potential paths. Classical physics would suggest the traveler takes one definitive route. Quantum mechanics revealed something far more radical. The traveler simultaneously explores every possible path, only resolving into a single trajectory when observed. Dr. Wilhelm Kreutzer loved to use musical metaphors. Quantum mechanics is like a cosmic jazz performance, he would explain. The musicians don't follow a fixed score. They create reality in the moment through improvisation and interaction. The Schrödinger's cat thought experiment became a powerful metaphorical tool. Imagine a cat in a sealed box, simultaneously alive and dead, not just unknown, but literally existing in multiple states at once. It was a perfect illustration of quantum superposition, the idea that possibility is the fundamental state of reality. Dr. Ilara Winters saw these metaphors as more than just explanatory tools. Metaphors are not simplifications, she would argue. They are windows into a deeper understanding. They allow us to perceive realities that mathematical equations alone cannot communicate. Consider the metaphor of quantum entanglement. Imagine two dancers, perfectly synchronized, connected by an invisible thread. No matter how far apart they move, their movements remain mysteriously linked. Measure the state of one, and the other instantaneously reflects that change. Dr. Marcus Holloway would dismiss such metaphorical explanations. This is poetry, not science, he would thunder during academic conferences. But the younger generation understood something profound, that metaphors were not just explanations, but ways of perceiving reality itself. The wave-particle duality became a metaphorical exploration of identity. Imagine a being that could simultaneously be a wave and a particle, fluid and fixed, spread out and concentrated depending on how it was perceived. It was a metaphor for the fundamental fluidity of existence. Quantum probability transformed into a metaphor of human potential. Imagine a life where every possibility exists simultaneously, where choice itself is a creative act of observation, where reality is not a fixed path, but a constant negotiation of potential. We are not passive observers, Dr. Elena Karoff would say. We are active participants in the creation of reality. Each observation is a creative act, each measurement a negotiation with the fundamental nature of existence. The metaphors revealed something profound. Reality was not a machine to be understood, but a living, breathing ecosystem of possibilities. Particles were not things, but potential. Observation was not a passive act, but a creative process. Dr. Antoinette Laurent captured this in a particularly poetic passage. Quantum mechanics teaches us that reality is not a noun, she wrote. It is a verb, not a fixed state, but a continuous process of becoming. As metaphors filled lecture halls and research facilities, humanity began to see the universe in an entirely new way. not as a fixed, deterministic system, but as a dynamic, interactive process of continuous creation. Reality would never be the same again. The resistance to quantum mechanics was not merely scientific, it was a philosophical rebellion against a fundamental reimagining of reality itself. Dr. Marcus Holloway represented the old guard of scientific understanding, a man whose entire intellectual edifice was threatened by the emerging quantum paradigm. With his meticulously trimmed beard and steel-rimmed glasses, he embodied the classical scientific worldview that was rapidly crumbling. Absolute nonsense, Holloway would thunder during academic conferences, his face turning an impressive shade of crimson. These quantum theorists are suggesting that reality is nothing more than a cosmic game of chance. Science is about precision, about certainty. But certainty was precisely what quantum mechanics was dismantling. The scientific establishment had built its entire understanding on the foundations of classical physics. Isaac Newton's mechanistic universe, where every particle moved with predictable precision, had been the cornerstone of scientific thought for centuries. The idea that reality might be fundamentally probabilistic, that observation itself could create reality, was more than a scientific challenge. It was an existential threat. Dr. Elena Karoff understood the deeper psychological resistance. Paradigm shifts are never just about evidence, she would explain. They're about letting go of our most fundamental beliefs about the nature of existence. Each of the quantum pioneers faced unique forms of institutional resistance. Grants were denied. Papers were rejected. Reputations were attacked. The more revolutionary the evidence, the more viciously the established scientific community fought back. Dr. Antoinette Laurent's groundbreaking work on quantum entanglement was initially dismissed as mathematical fantasy. Her experiments showed particles could be mysteriously linked across vast distances, instantaneously influencing each other regardless of space and time. To classical physicists, this was heresy. Dr. Wilhelm Kreutzer's mathematical models were equally threatening. His equations suggested that particles existed in multiple states simultaneously, only resolving into a definitive state through observation. It was as if reality itself was a grand improvisation, constantly reshaped by perception. The resistance wasn't just institutional, it was deeply personal. Many scientists had built entire careers on classical understanding. Admitting the possibility of quantum mechanics meant admitting that everything they thought they knew was fundamentally wrong. It was an intellectual and emotional challenge that few were prepared to face. Einstein himself, one of the founders of quantum theory, struggled with its implications. God does not play dice with the universe, he famously declared, refusing to accept the probabilistic nature of quantum mechanics. Even he, a revolutionary thinker, found the new understanding too radical to fully embrace. Dr. Alara Winters saw the deeper psychological dynamics. Scientific revolutions are always met with resistance, she would argue. Not because the evidence is weak, but because the new understanding threatens our most fundamental beliefs about reality. The philosophical implications were profound. If reality was fundamentally uncertain, what did that mean for human understanding, for free will, for our conception of consciousness? Some religious institutions saw quantum mechanics as a threat. Others saw it as a potential bridge between scientific and spiritual understanding. The idea that observation creates reality resonated with mystical traditions that had long suggested the participatory nature of human perception. Dr. Marcus Holloway represented the most vocal resistance. During a heated debate at the Berlin Imperial Academy, he denounced quantum mechanics as mathematical mysticism. His colleagues nodded in agreement, their worldview threatened by these radical ideas. But the younger generation of scientists saw something magnificent. They were uncovering a fundamental truth about reality, a truth far more complex and wonderful than anyone had ever imagined. Dr. Elena Karoff captured the essence of this transformation. Scientific progress is never about confirming what we already know, she would say. It's about being willing to completely destroy our existing understanding when new evidence demands it. As resistance mounted, the quantum pioneers pressed forward. Each experiment, each mathematical model was a challenge to the existing scientific worldview. They were not just researchers, they were revolutionaries, rewriting the fundamental understanding of reality itself. The old scientific order was crumbling. In its place, a new understanding was emerging, fluid, dynamic, infinitely more complex and wonderful than anyone had ever imagined. Reality would never be the same again. Mathematical exploration reached new heights of complexity, transforming abstract symbols into windows, into the fundamental nature of reality. The research facility's advanced mathematics wing looked more like an artist's studio than a traditional scientific laboratory. Massive chalkboards covered every wall, filled with intricate equations that seemed to breathe with their own mysterious life. Each symbol was not merely a mathematical notation, but a portal to understanding the universe's most profound secrets. Dr. Wilhelm Kreutzer stood at the center of this mathematical sanctuary, his fingers covered in chalk dust, eyes blazing with intellectual passion. Mathematics is not just a language of description, he would tell his students. It is the fundamental architecture of reality itself. The wave function, represented by the Greek letter psi, became the most profound mathematical construct in quantum mechanics. It was more than an equation. It was a comprehensive description of a quantum system's entire possible state of existence. Imagine an equation that could describe not just what is, but every possible thing that could be. An equation that represented pure potential. The Schrödinger equation emerged as the fundamental mathematical language of quantum mechanics. IH bar, partial derivative of psi with respect to t equals h bar psi. A deceptively simple notation that contained the keys to understanding the most profound mysteries of the universe. Dr. Elena Karoff would break down the equation with remarkable clarity. The complex I represented the imaginary number, was the reduced Planck constant. Pepst T described how the wave function changed over time, and H represented the system's total energy, the Hamiltonian operator. Complex numbers became the fundamental language of quantum description. Unlike simple real numbers, these mathematical constructs suggested multiple dimensions of possibility. A number that included both real and imaginary components became a metaphor for the quantum understanding of reality. Dr. Antoinette Laurent specialized in translating these abstract mathematical concepts into tangible understanding. Think of it like a cosmic probability map, she would explain. Every possible outcome exists simultaneously, with different probabilities of being realized. Quantum field theory took mathematical exploration to even more profound levels. It suggested that particles were not fundamental entities, but excitations in underlying quantum fields that permeated all of space. The mathematics revealed a universe far more interconnected than anyone had imagined. The mathematical models developed by Kreutzer and his colleagues showed how particles could be described as probability waves. Each equation was a map of possibility, showing not where something is, but where it could be. Dr. Marcus Holloway continued to rail against these mathematical abstractions. "This is numerology, not science," he would thunder during academic conferences. But the younger generation of scientists saw something magnificent. They were uncovering the mathematical language of reality itself. Operator theory became a crucial mathematical framework. Quantum mechanics introduced operators that did far more than simple multiplication. The position operator, momentum operator, and energy operator transformed mathematical understanding, showing how abstract mathematical constructs could reveal fundamental properties of reality. The mathematical exploration revealed profound symmetries. Equations that seemed unrelated would suddenly reveal deep, interconnected patterns. It was as if mathematics was not just describing the universe, but revealing its fundamental design. Dr. Ilara Winters saw the deeper philosophical implications. Mathematics is the language through which the universe speaks to us, she would argue during late-night discussions. Each equation is a window into a deeper understanding of reality. Quantum mechanics transformed mathematics from a tool of description to a method of exploration. Each equation was a journey into the unknown, a probe into the fundamental nature of existence. The practical implications were profound. Mathematical models suggested entire realms of possibility that classical physics had never imagined. Quantum computing, quantum encryption, advanced materials, all emerged from this mathematical exploration. As equations filled research notebooks and covered chalkboard after chalkboard, humanity stood on the brink of a mathematical revelation. The universe was not a machine to be understood, but a living, breathing, mathematical symphony waiting to be heard. Dr. Elena Karov would often quote the mathematician Johannes Kepler. "Geometry is one and eternal, a reflection from the mind of God." Now, quantum mechanics was suggesting that mathematics was not just a reflection, but the very language of creation itself. Reality would never be the same again. The human consciousness became the next great frontier of quantum exploration, a realm where scientific understanding collided with the most profound philosophical questions about existence itself. Dr. Elena Karov's research had always existed at the intersection of physics and philosophy, but her latest work pushed the boundaries of human comprehension. The mysterious relationship between observation and reality now turned inward, examining the fundamental nature of human perception and consciousness. In the small, carefully controlled research facility in New Caledonia, a series of groundbreaking experiments began to unravel the quantum nature of consciousness. Dr. Ilara Winters had long theorized that consciousness was not merely a product of neural activity, but a fundamental quantum process that participated in the creation of reality. Their initial experiments were deceptively simple, yet profoundly complex. Subjects were placed in carefully designed quantum measurement environments where their observations and mental states were meticulously tracked. The goal was to understand how consciousness itself might interact with quantum systems. Dr. Antoinette Laurent had developed sophisticated measuring instruments that could detect the most minute quantum interactions. These were not traditional brain scanners or EEG machines, but intricate quantum sensors that could map the subtle interactions between consciousness and quantum states. "We are not just measuring brain activity," Laurent would explain to her increasingly fascinated research team. "We are exploring the fundamental interface between perception and reality itself." The first breakthrough came unexpectedly. During a routine experiment measuring quantum entanglement, researchers discovered something extraordinary. The mental state of the observer seemed to have a measurable impact on quantum systems, beyond what could be explained by classical observation. Subjects were asked to focus their consciousness on quantum systems, particles existing in multiple states. Preliminary results suggested that focused mental intention could subtly influence the probability of quantum state resolution. It was as if consciousness itself was a fundamental force that could negotiate with the quantum realm. Dr. Wilhelm Kreuzer's mathematical models provided a theoretical framework for these seemingly impossible observations. His equations suggested that consciousness might be a fundamental quantum process, not confined to the brain, but existing as a fundamental property of reality itself. "Imagine consciousness as a quantum field," Kreutzer would explain during intense late-night discussions. "Not a thing, but a process of continuous creation and observation. A living, breathing ecosystem of possibility." The implications were staggering. If consciousness could interact with quantum systems, it suggested that human perception was not a passive act of receiving information, but an active process of participating in the creation of reality. Dr. Marcus Holloway, the perennial skeptic, continued to rail against these ideas. "This is mysticism," he would thunder during academic conferences. "Science cannot prove such metaphysical nonsense." But the experimental evidence was becoming increasingly difficult to dismiss. Quantum biology provided additional insights. Researchers discovered that biological systems might be using quantum mechanisms in ways never before understood. Photosynthesis, bird navigation, even the complex processes of neural communication seem to involve quantum-level interactions. The human brain, it turned out, might be a far more sophisticated quantum computer than any artificial system. Neural networks appeared to exhibit quantum coherence, maintaining delicate quantum states that allowed for unprecedented computational complexity. Dr. Elena Karoff saw these discoveries as more than just scientific breakthroughs. "We are not separate from the universe," she would argue. "We are the universe experiencing itself. Consciousness is not something that happens in our brains. It is a fundamental process of reality's continuous creation." The research challenged every existing understanding of human perception. If consciousness could influence quantum states, what did that mean for free will, for human potential, for our understanding of reality itself? Meditation traditions had spoken for millennia about the interconnectedness of consciousness. Now, quantum mechanics was providing a scientific framework for understanding these ancient insights. The quantum consciousness experiments were just the beginning. Each discovery opened up new questions, new possibilities. The boundary between observer and observed, between consciousness and reality, was becoming increasingly blurred. Dr. Ilara Winters captured the essence of their discoveries in a profound statement. "We are not just discovering the universe," she would say. "We are negotiating its very nature. Consciousness is not a passive process of perception, but an active dialogue with the fundamental fabric of reality." As research continued, humanity stood on the brink of a profound revelation. Consciousness was not something that happened in isolation. It was a fundamental quantum process, a creative force that participated in the continuous creation of reality. The universe was revealing its true nature, and nothing would ever be the same again. The intersection of quantum mechanics and ecological systems opened up an entirely new frontier of scientific understanding, revealing a world far more interconnected and dynamic than anyone had previously imagined. Dr. Elena Karov's research facility had expanded its focus beyond traditional physics, exploring the quantum foundations of biological and ecological systems. What emerged was a revolutionary understanding of life itself, not as a collection of discrete organisms, but as a complex, interconnected quantum ecosystem. Dr. Antoinette Laurent had been particularly instrumental in this groundbreaking research. Her work suggested that living systems were not just subject to quantum principles, but actively utilized quantum mechanisms in ways that defied classical biological understanding. The first major breakthrough came from an unexpected source: photosynthesis. For decades, scientists had struggled to explain the remarkable efficiency of plant energy conversion. Classical physics could not account for how plants could capture and transfer solar energy with such incredible precision. Quantum mechanics revealed a stunning explanation. The process of photosynthesis appeared to leverage quantum coherence, a phenomenon where quantum states remained stable long enough to facilitate incredibly efficient energy transfer. It was as if plants were performing complex quantum computations at the molecular level, exploring multiple energy pathways simultaneously. Imagine a quantum algorithm happening within every leaf, Dr. Laurent would explain during her lectures, her eyes sparkling with intellectual excitement. The plant is not just absorbing sunlight, it is negotiating energy transfer through a sophisticated quantum process. Dr. Wilhelm Kreutzer's mathematical models provided the theoretical framework. His equations suggested that biological systems might be using quantum superposition and entanglement in ways that fundamentally challenged existing understanding of life itself. Migratory birds presented another fascinating quantum ecological puzzle. How could birds navigate with such incredible precision across thousands of miles? Researchers discovered that birds might be using quantum entanglement in their navigational systems, sensing the Earth's magnetic field through quantum-level interactions in their cellular structures. Dr. Ilara Winters saw these discoveries as more than just biological curiosities. "We are uncovering a fundamental truth," she would argue during late-night discussions. "Life is not a mechanical process. It is a quantum conversation with the environment." The research extended to more complex ecological systems. Ecosystem interactions that had previously seemed random now revealed intricate quantum-level communications. Plants appeared to send chemical signals through quantum-coherent networks, creating communication systems that transcended classical understanding of biological interaction. Dr. Marcus Holloway, the perpetual skeptic, continued to challenge these ideas. "This is pure speculation," he would thunder during academic conferences. "You cannot reduce complex ecological systems to quantum mechanics." But the experimental evidence was becoming increasingly difficult to dismiss. Quantum ecology suggested that ecosystems were not just collections of individual organisms, but interconnected quantum networks. Each organism, each interaction, became part of a complex quantum dialogue with the environment. The implications were profound. If ecological systems operated through quantum principles, it suggested a fundamental reimagining of life itself. Organisms were not isolated entities, but participants in a continuous quantum conversation. Dr. Elena Karov's team developed increasingly sophisticated measurement techniques. Quantum sensors could now detect the most minute interactions between organisms, revealing communication networks that operated at quantum scales. Fungal networks in forests provided a particularly compelling example. What had once been understood as simple root connections now revealed themselves as complex quantum communication systems. Trees appeared to share resources and information through intricate quantum coherent networks, creating what some researchers began to call the Wood Wide Web. The research challenged fundamental assumptions about competition and cooperation in nature. Ecological interactions were not just about survival of the fittest, but about complex quantum negotiations between different life forms. "We are discovering," Dr. Karov would say, "that life is not a battle, but a conversation, a continuous quantum dialogue between organisms and their environment." Practical applications began to emerge. Understanding quantum ecological principles could revolutionize approaches to agriculture, conservation, and environmental management. Imagine crop systems designed to leverage quantum energy transfer, or conservation strategies that recognize the deep quantum interconnectedness of ecosystems. The boundary between physics, biology, and ecology was dissolving. Quantum mechanics was revealing a universe far more interconnected, far more alive than anyone had previously imagined. As research continued, humanity stood on the brink of a profound revelation. Life was not a mechanical process, but a dynamic quantum conversation, a continuous negotiation between organisms and the fundamental fabric of reality. The universe was revealing its true nature, and nothing would ever be the same again. The global political landscape trembled on the precipice of a technological revolution that threatened to reshape the fundamental balance of power. Quantum technologies were no longer theoretical abstractions, but potent instruments of geopolitical transformation. In the secure research facilities scattered across the world's most advanced nations, a silent arms race was emerging. Quantum computing, quantum encryption, quantum sensing. Each breakthrough carried the potential to upend centuries of strategic calculation. Dr. Elena Karov understood the profound implications better than most. Her research facility in New Caledonia had become an unexpected nexus of geopolitical tension. Governments and intelligence agencies from multiple nations were keenly interested in the quantum technologies being developed. Dr. Wilhelm Kreutzer's mathematical models had revealed something extraordinary. Quantum computing wasn't just a faster version of classical computing. It was an entirely new paradigm of information processing that could crack encryption systems thought to be unbreakable, simulate complex global systems with unprecedented accuracy, and potentially predict economic and political trends with mind-bending precision. Imagine a computer, Kreutzer would explain during classified briefings, that can simultaneously explore millions of potential scenarios, not sequentially, but truly simultaneously. It's not just a technological advancement, it's a fundamental reimagining of computational possibility. The national security implications were staggering. A quantum computer could potentially decrypt decades of classified communications, model complex global scenarios with near-perfect accuracy, and provide strategic insights that would transform military and diplomatic calculations. Dr. Antoinette Laurent's work in quantum communication had produced encryption technologies that promised absolute security. Quantum entanglement allowed for communication channels that were theoretically impossible to intercept. Any attempt to observe the quantum communication would fundamentally alter its state, making traditional espionage techniques obsolete. But the most profound quantum technologies were emerging in unexpected domains. Quantum sensing could detect underground structures with unprecedented precision. Submarine movements, hidden military installations, even geological resources could be mapped with a level of detail that would revolutionize intelligence gathering. Dr. Ilara Winters saw the deeper philosophical implications. Technology is never neutral, she would argue, during intense strategy discussions. Each quantum breakthrough is a negotiation with the fundamental nature of reality itself. And in that negotiation, power is constantly being redistributed. The global powers understood this implicitly. Research facilities in the United States, China, Russia, and European Union were pouring unprecedented resources into quantum research. It was more than technological competition. It was a fundamental struggle to control the emerging paradigm of technological possibility. Quantum artificial intelligence represented perhaps the most transformative potential. Machines that could not just calculate, but explore multiple potential realities simultaneously. Intelligences that could process information in ways that transcended classical computational limits. Military strategists were particularly fascinated. Quantum technologies promised weapons systems that could make traditional military calculations obsolete. Predictive systems that could model conflict scenarios with unprecedented accuracy. Communication systems that were fundamentally secure. Dr. Marcus Holloway, who had long been skeptical of quantum theories, now found himself in classified briefings that explored these revolutionary technologies. "We are not just developing new tools," one intelligence director had explained to him. "We are rewriting the fundamental language of strategic calculation." The economic implications were equally profound. Quantum technologies could reshape entire industries. Financial modeling, drug discovery, materials engineering. Each field stood on the brink of a fundamental transformation. Quantum sensing could revolutionize resource exploration. Imagine geological surveys that could map underground resources with molecular-level precision. Oil deposits, mineral reserves, water resources. Nothing could remain hidden. Quantum communication technologies promised to reshape global telecommunications. Encryption systems that were fundamentally secure. Communication channels that could transmit information instantaneously, regardless of distance. The geopolitical landscape was becoming a complex quantum system. Traditional notions of national power, military might, economic strength, technological capability were being fundamentally reimagined. Dr. Elena Karoff understood the profound responsibility that came with these discoveries. We are not just developing technologies, she would argue in private strategy meetings. We are learning to negotiate with the fundamental nature of reality itself. As quantum technologies continued to emerge, the world stood on the brink of a fundamental transformation. The balance of global power was no longer about physical resources or industrial might. It was about the ability to understand, manipulate, and negotiate with the fundamental quantum nature of reality. The universe was revealing its true nature, and nothing would ever be the same again. The intersection of quantum mechanics and artistic expression became a revolutionary frontier of human creativity, challenging the most fundamental boundaries between perception, imagination, and reality. Dr. Eleanor Karoff's research facility had begun an unprecedented collaboration with artists, musicians, and creative professionals, exploring how quantum principles could transform the very nature of artistic creation. What emerged was a radical reimagining of creativity itself, not as a purely human endeavor, but as a quantum dialogue between consciousness, possibility, and manifestation. Dr. Antoinette Laurent had been particularly instrumental in bridging the gap between scientific precision and artistic imagination. Her work suggested that artistic creation was not a linear process, but a quantum exploration of potential realities. The first major breakthrough came from an experimental music ensemble led by a quantum physicist turned composer. Using quantum random number generators and sophisticated quantum sensing technologies, they created music that was fundamentally unpredictable, compositions that existed in a state of quantum superposition until the moment of performance. Imagine a musical piece that is simultaneously every possible version of itself, the lead composer would explain during mind-bending performances. The act of listening creates the specific musical reality. Dr. Wilhelm Kreutzer's mathematical models provided a theoretical framework for understanding creativity as a quantum process. His equations suggested that artistic inspiration might be a form of quantum entanglement, a mysterious connection between imagination and potential realities. Visual artists began experimenting with quantum-inspired creation techniques. Painters developed methods of working with quantum uncertainty, creating artworks that literally changed based on the observer's perception. Quantum sensors embedded in canvases would shift colors, textures, and compositions in real time, responding to the quantum state of the viewer's consciousness. Dr. Ilara Winters saw these developments as more than artistic curiosities. We are discovering, she would argue during late-night discussions, that creativity is not about reproducing existing reality. It's about negotiating potential realities. Quantum theater became an entirely new art form. Performances were designed as quantum events where multiple narrative possibilities existed simultaneously. Actors would perform multiple potential storylines concurrently, with the audience's collective perception determining the final narrative trajectory. Digital artists developed quantum rendering technologies that could generate images existing in multiple states simultaneously. A single artwork would be a probability cloud of visual possibilities, resolving into a specific image only when viewed. Dr. Marcus Holloway, perpetually skeptical, continued to challenge these artistic explorations. "This is nonsense," he would thunder. "Art requires skill, not quantum mysticism." But the creative community saw something magnificent. They were uncovering a fundamental truth about creativity, that imagination itself might be a quantum process of continuous creation. Literature took on new dimensions. Quantum-inspired writers developed narrative techniques that mimicked quantum superposition, books that existed in multiple potential storylines simultaneously, with reader perception determining the final narrative arc. Architects began designing quantum-responsive spaces, buildings that could subtly shift their structural characteristics based on the quantum state of their occupants. Spaces that were not fixed, but in a constant state of potential transformation. Choreographers explored quantum movement principles, dance performances that existed in multiple potential configurations, with the performers and audience's collective consciousness negotiating the final form of the performance. The collaboration between scientists and artists revealed something profound. Creativity was not about reproducing existing reality, but about exploring potential realities. Each artistic act became a quantum negotiation between imagination and possibility. Emerging technologies allowed for unprecedented creative exploration. Quantum random number generators became tools of artistic creation. Quantum sensing technologies transformed into instruments of creative expression. Dr. Elena Karoff saw these developments as more than artistic innovation. "We are learning," she would say, "that creativity is a fundamental process of reality's continuous creation. Art is not a reflection of reality. It is a negotiation with reality itself." The boundaries between science, philosophy, and art were dissolving. Quantum mechanics was revealing that creativity was not a human invention, but a fundamental process of cosmic exploration. As research and artistic exploration continued, humanity stood on the brink of a profound revelation. Creativity was not a passive process of representation, but an active dialogue with the fundamental fabric of reality. The universe was revealing its true nature, and nothing would ever be the same again. The ancient wisdom traditions of human civilization found themselves in an unexpected dialogue with quantum mechanics, revealing a profound convergence between mystical insights and scientific understanding that challenged the very foundations of human perception. Dr. Elena Karoff's research facility had become an unexpected bridge between scientific exploration and spiritual wisdom. What had once been considered separate domains of human understanding were now revealing themselves as complementary pathways to comprehending the fundamental nature of reality. Dr. Ilara Winters had been particularly instrumental in this groundbreaking exploration. Her background in both physics and comparative philosophy positioned her uniquely to unravel the deep connections between quantum mechanics and millennia-old spiritual traditions. Buddhist meditation practices of non-duality suddenly found scientific validation through quantum principles. The traditional Buddhist concept of interconnectedness, that no entity exists in isolation, that everything is fundamentally connected, aligned remarkably with quantum entanglement theories. Dr. Wilhelm Kreutzer's mathematical models provided a scientific framework for understanding these ancient insights. His equations suggested that the fundamental nature of reality was far more fluid, far more interconnected than classical physics had ever imagined. "Imagine consciousness as a fundamental field," Kreutzer would explain during interdisciplinary conferences, "not confined to individual beings, but as a continuous process of interaction and potential. Indigenous wisdom traditions that had long spoken about the participatory nature of human perception found themselves vindicated by quantum mechanical discoveries. Native American, Aboriginal, and other indigenous philosophies that viewed humans as participants in, rather than observers of, reality now had a scientific language to articulate their understanding. Dr. Antoinette Laurent's research into quantum consciousness revealed startling parallels with mystical traditions. Meditation practices that spoke of transcending individual consciousness now found scientific support in quantum theories of interconnected awareness. The Hindu concept of Maya, the idea that individual perception creates a limited version of reality, resonated deeply with quantum mechanics' understanding of observation creating reality. The notion that reality is not fixed, but constantly negotiated through perception, found a precise scientific articulation. Taoist philosophy, with its emphasis on the dynamic interplay of opposing forces, found remarkable alignment with quantum principles of complementarity and uncertainty. The Taoist concept of Wu Wei, action through non-action, or flowing with the fundamental nature of reality, suddenly took on a profound scientific significance. Dr. Marcus Holloway continued to rail against these philosophical interpretations. "This is mysticism," he would thunder during academic conferences. "Science is about objective measurement, not spiritual speculation." But the evidence was becoming increasingly difficult to dismiss. Meditation researchers discovered that advanced practitioners could demonstrate measurable quantum-level interactions that transcended classical understanding. Tibetan Buddhist monks demonstrated extraordinary abilities to maintain quantum coherence in their neural systems, suggesting that consciousness might be a fundamental quantum process. Shamanic traditions that spoke of interconnectedness and the ability to perceive multiple realities found scientific validation in quantum superposition principles. The idea that reality is not fixed, but exists in multiple potential states, aligned perfectly with shamanic understanding of consciousness. The practical implications were profound. Mindfulness practices, meditation techniques, and spiritual disciplines were no longer seen as mere cultural practices, but as sophisticated technologies for navigating quantum reality. Dr. Elena Karov saw these discoveries as more than academic curiosities. "We are not separate from the universe," she would argue during intense philosophical discussions. "We are the universe experiencing itself. Consciousness is not something that happens in our brains. It is a fundamental process of reality's continuous creation." Quantum mechanics was revealing a fundamental truth that mystical traditions had understood for millennia, that reality is not a fixed stage, but a dynamic, interactive process of continuous creation. Religious traditions that had long spoken about the participatory nature of human consciousness found themselves at the forefront of a scientific revolution. The boundaries between scientific observation and spiritual insight were dissolving. Interfaith dialogues took on new significance. Scientific conferences began to include spiritual leaders, philosophers, and wisdom tradition practitioners. The conversation was no longer about conflict between science and spirituality, but about a deeper understanding of reality's fundamental nature. As research continued, humanity stood on the brink of a profound revelation. Consciousness was not confined to individual beings, but a fundamental quantum process of continuous creation and exploration. The universe was revealing its true nature, and nothing would ever be the same again. The exploration of quantum mechanics in human health and medicine represented a fundamental reimagining of biological understanding, transforming medical science from a practice of treating symptoms to a sophisticated dialogue with the fundamental nature of life itself. Dr. Elena Karov's research facility had become a crucible of medical innovation, where quantum principles were revealing the intricate, dynamic nature of human biological systems. What had once been understood as fixed biological mechanisms now emerged as complex, interconnected quantum networks of extraordinary sophistication. Dr. Antoinette Laurent had been particularly instrumental in developing quantum medical diagnostics. Her breakthrough technologies could detect cellular interactions at quantum scales, revealing disease processes long before traditional diagnostic methods could identify the slightest deviation from health. Imagine medical scanning that doesn't just look at the body, Laurent would explain during groundbreaking presentations, but engages in a quantum dialogue with cellular systems. We're not just observing, we're participating in the body's healing process. Dr. Wilhelm Kreutzer's mathematical models provided a theoretical framework for understanding health as a dynamic quantum system. His equations suggested that biological systems were not mechanical processes, but complex quantum networks of continuous interaction and potential. Quantum cellular imaging revealed the human body in ways that defied classical medical understanding. Cells were not fixed entities, but dynamic quantum systems constantly negotiating their state of being. Disease could now be understood as a disruption in these quantum communication networks, rather than a simple mechanical breakdown. Genetic research took on entirely new dimensions. Quantum principles suggested that genetic expression was far more fluid than previously understood. Genes were not fixed scripts, but dynamic quantum possibilities that could be influenced by consciousness, environment, and subtle quantum interactions. Cancer research experienced a revolutionary transformation. Quantum-level diagnostics could detect cellular mutations at unprecedented scales, identifying potential cancerous developments at the earliest possible moment. Treatment shifted from aggressive intervention to precise quantum negotiation with cellular systems. Neurological research uncovered the quantum nature of brain function. Neural networks were not just electrical systems, but sophisticated quantum computation devices. Consciousness itself emerged as a quantum process, with thoughts and perceptions existing as probability waves of potential experience. Dr. Ilara Winters saw these discoveries as more than medical breakthroughs. We are learning, she would argue during intense research discussions, that healing is not about fighting against the body, but about creating a quantum dialogue of potential wellness. Quantum pharmacology emerged as a revolutionary field. Drug development shifted from a one-size-fits-all approach to precise quantum-level interventions. Medications could be designed to interact with specific quantum states of cellular systems, targeting diseases with unprecedented precision. Personalized medicine reached new heights of sophistication. Each patient's unique quantum signature could be mapped, allowing for treatment approaches tailored to their specific quantum biological configuration. Dr. Marcus Holloway, perpetually skeptical, continued to challenge these medical innovations. "This is pure speculation," he would thunder during medical conferences. "Medicine is about empirical observation, not quantum mysticism." But the experimental evidence was becoming increasingly difficult to dismiss. Quantum healing practices began to bridge traditional medical approaches with a more holistic understanding of biological systems. Meditation, consciousness practices, and quantum-informed therapeutic approaches showed remarkable potential in supporting the body's healing processes. Immunology was completely transformed. The immune system was revealed as a sophisticated quantum communication network, with immune responses understood as complex quantum negotiations rather than simple mechanical defenses. Mental health treatment took on new dimensions. Psychological conditions could be understood as disruptions in quantum neural networks, with treatment approaches designed to restore quantum coherence in neural systems. Regenerative medicine discovered quantum principles of cellular communication that could potentially reverse aging processes. Cells were not fixed in their developmental trajectory, but existed in a state of continuous quantum potential. Dr. Elena Karoff captured the essence of these discoveries in her most profound statement: "We are not treating bodies. We are engaging in a quantum dialogue with the fundamental nature of life itself." The boundaries between physics, biology, and medicine were dissolving. Quantum mechanics was revealing that health was not a fixed state, but a continuous process of quantum negotiation and potential. As research continued, humanity stood on the brink of a profound revelation. The human body was not a machine, but a living, breathing quantum ecosystem of extraordinary complexity and potential. The universe was revealing its true nature, and nothing would ever be the same again. The exploration of quantum mechanics in environmental systems represented a profound reimagining of our understanding of planetary dynamics, revealing the Earth as a complex, interconnected quantum system, far more intricate and responsive than anyone had previously imagined. Dr. Elena Karoff's research facility had become a global nexus of environmental quantum research, bridging disciplines and challenging fundamental assumptions about ecological interactions, climate systems, and planetary evolution. Dr. Antoinette Laurent had developed groundbreaking quantum sensing technologies that could map environmental interactions at unprecedented scales. These quantum sensors revealed planetary systems, not as fixed mechanisms, but as dynamic, interconnected quantum networks of extraordinary complexity. "We are not just observing the environment," Laurent would explain during revolutionary presentations. "We are engaging in a quantum dialogue with the planetary ecosystem. Each measurement is a negotiation, each observation a creative act of understanding." Dr. Wilhelm Kreutzer's mathematical models provided a theoretical framework for understanding environmental systems as quantum probability networks. His equations suggested that ecological interactions were far more fluid, far more interconnected than classical environmental science had ever conceived. Climate research underwent a fundamental transformation. Quantum models revealed climate systems as complex quantum probability fields where multiple potential environmental trajectories existed simultaneously. Predictive models shifted from linear projections to sophisticated quantum probability mappings that could explore multiple potential planetary futures. Quantum sensing technologies could detect environmental changes at molecular and quantum scales. Minute shifts in ecological systems, previously undetectable, became readable as complex quantum communications. Forest ecosystems emerged as sophisticated quantum communication networks, with trees and organisms engaging in intricate quantum exchanges of information and energy. Ocean systems revealed themselves as dynamic quantum ecosystems. Quantum-level sensing could track marine interactions with unprecedented precision, revealing complex communication networks among marine organisms that transcended classical understanding of ecological interaction. Dr. Ilara Winters saw these discoveries as more than environmental research. We are learning, she would argue during intense research discussions, that the planet is not a collection of separate systems, but a living, breathing, quantum organism. Each interaction is a negotiation, each observation a creative act of planetary understanding. Quantum geological research transformed understanding of planetary evolution. Tectonic processes could now be understood as quantum probability fields, with multiple potential geological trajectories existing simultaneously. Earthquake prediction shifted from statistical modeling to quantum probability mapping. Atmospheric research revealed the atmosphere as a sophisticated quantum communication system. Air currents, weather patterns, and climatic interactions emerged as complex quantum negotiations rather than simple mechanical processes. Dr. Marcus Holloway continued to challenge these environmental interpretations. "This is environmental mysticism," he would thunder during academic conferences. "Science requires objective, measurable data." But the experimental evidence was becoming increasingly difficult to dismiss. Biodiversity research took on new dimensions. Ecosystem interactions could be understood as quantum communication networks, with species engaging in complex quantum exchanges of information and energy. Biodiversity emerged not as a competitive system, but as a sophisticated quantum dialogue of planetary potential. Quantum-informed conservation strategies suggested entirely new approaches to environmental protection. Instead of viewing ecosystems as fixed systems to be preserved, environmental management became a process of quantum negotiation, supporting the natural quantum potential of ecological systems. Renewable energy research discovered quantum principles of energy exchange that could revolutionize sustainable technologies. Photosynthesis, wind energy, and solar technologies could be understood and engineered through quantum interaction principles. Agricultural systems were transformed. Crop management shifted from mechanical intervention to quantum-informed ecological dialogue. Understanding the quantum nature of soil ecosystems, plant interactions, and environmental exchanges suggested revolutionary approaches to sustainable agriculture. Planetary mapping technologies could now track environmental changes at quantum scales. Minute shifts in ecological systems, previously undetectable, became readable as complex quantum communications. Dr. Elena Karov captured the essence of these discoveries in her most profound statement. "We are not separate from the planetary ecosystem. We are participants in a continuous quantum dialogue of planetary potential. The boundaries between physics, ecology, and environmental science were dissolving. Quantum mechanics was revealing that the planet was not a fixed system, but a living, breathing quantum ecosystem of extraordinary complexity and potential." As research continued, Humanity stood on the brink of a profound revelation. The Earth was not a machine, but a living, breathing quantum organism of interconnected possibility. The universe was revealing its true nature, and nothing would ever be the same again. The exploration of quantum mechanics in economic systems represented a fundamental reimagining of human interactions, transforming economic understanding from a mechanistic model of exchange to a dynamic, probabilistic dialogue of collective potential. Dr. Elena Karov's research facility had become an unexpected crucible of economic innovation, where quantum principles were revealing the intricate, interconnected nature of human economic interactions. What had once been understood as fixed market mechanisms now emerged as complex, dynamic quantum networks of extraordinary sophistication. Dr. Antoinette Laurent had developed groundbreaking quantum economic modeling technologies that could map economic interactions at unprecedented scales. These quantum economic sensors revealed market systems not as predictable mechanisms, but as complex probability fields of human potential and interaction. We are not just analyzing markets, Laurent would explain during revolutionary economic conferences. We are engaging in a quantum dialogue with human economic potential. Each economic interaction is a negotiation, each transaction a creative act of collective value creation. Dr. Wilhelm Kreutzer's mathematical models provided a theoretical framework for understanding economic systems as quantum probability networks. His equations suggested that economic interactions were far more fluid, far more interconnected than classical economic theories had ever conceived. Traditional economic models of supply and demand were transformed. Economic value emerged not as a fixed quantity, but as a quantum probability field of potential value creation. Markets were revealed as complex quantum communication networks where multiple economic trajectories existed simultaneously. Quantum financial technologies could detect economic shifts at microscopic scales. Minute changes in economic interactions, previously undetectable, became readable as complex quantum communications of collective human potential. Investment strategies underwent a fundamental transformation. Quantum probability modeling allowed for unprecedented insight into market potentials. Traditional risk assessment gave way to sophisticated quantum probability mapping that could explore multiple potential economic futures simultaneously. Dr. Ilara Winters saw these discoveries as more than economic research. We are learning, she would argue, during intense research discussions, that economic value is not a fixed quantity. It is a dynamic quantum process of collective human potential. Cryptocurrency and blockchain technologies found a profound theoretical foundation in quantum mechanics. Economic exchanges could now be understood as quantum information transfers, with value existing in a state of quantum superposition until the moment of transaction. Labor market dynamics were completely reimagined. Human potential was no longer viewed as a fixed resource, but as a quantum field of continuous possibility. Employment became understood as a dynamic quantum negotiation of collective potential rather than a simple transactional exchange. Dr. Marcus Holloway continued to challenge these economic interpretations. "This is economic mysticism," he would thunder during academic conferences. "Economics requires objective, measurable data." But the experimental evidence was becoming increasingly difficult to dismiss. Global economic modeling took on new dimensions. Economic interactions could be understood as quantum communication networks, with different economic systems engaging in complex quantum exchanges of value and potential. Quantum-informed economic policies suggested entirely new approaches to economic management. Instead of viewing economic systems as fixed mechanisms to be controlled, economic strategy became a process of quantum negotiation, supporting the natural quantum potential of human economic interaction. Poverty reduction strategies were transformed. Understanding economic systems as quantum probability fields suggested revolutionary approaches to economic development that focused on supporting collective human potential rather than mechanical resource distribution. International trade emerged as a sophisticated quantum dialogue of economic potential. Economic exchanges were no longer viewed as zero-sum interactions, but as complex quantum negotiations of collective value creation. Artificial intelligence in economic modeling could now explore multiple economic trajectories simultaneously. Machine learning algorithms evolved from predictive tools to quantum probability explorers, mapping complex economic potential. Resource allocation strategies shifted dramatically. Economic value was no longer seen as a fixed quantity to be distributed, but as a dynamic quantum field of collective potential waiting to be realized. Dr. Elena Karoff captured the essence of these discoveries in her most profound statement. We are not managing economic systems. We are participating in a continuous quantum dialogue of human economic potential. The boundaries between physics, economics, and human potential were dissolving. Quantum mechanics was revealing that economic value was not a fixed system, but a living, breathing quantum ecosystem of extraordinary complexity and potential. As research continued, humanity stood on the brink of a profound revelation. Economic systems were not machines, but living, breathing quantum networks of human collective potential. The universe was revealing its true nature, and nothing would ever be the same again. The exploration of quantum mechanics in historical understanding represented a profound reimagining of human temporal experience, challenging fundamental assumptions about the nature of time, memory, and collective human experience. Dr. Elena Karoff's research facility had become an unexpected crucible of historical quantum research, where traditional linear understanding of time gave way to a more complex, multi-dimensional perception of human experience. What had once been understood as a fixed historical narrative now emerged as a dynamic quantum field of collective memory and potential. Dr. Antoinette Laurent had developed groundbreaking quantum historical mapping technologies that could explore historical interactions at unprecedented scales. These quantum historical sensors revealed human history not as a linear progression, but as a complex probability field of interconnected human experiences. We are not just studying the past, Laurent would explain during revolutionary interdisciplinary conferences. We are engaging in a quantum dialogue with human collective memory. Each historical investigation is a negotiation, each interpretation a creative act of collective understanding. Dr. Wilhelm Kreutzer's mathematical models provided a theoretical framework for understanding historical systems as quantum probability networks. His equations suggested that historical events were far more fluid, far more interconnected than traditional historical methodologies had ever conceived. Historical research transformed from a process of linear documentation to a sophisticated exploration of quantum probability fields. Traditional historical narratives gave way to complex mappings of multiple potential historical trajectories, each existing simultaneously in a state of quantum superposition. Quantum memory research revealed human memory not as a fixed record, but as a dynamic quantum process of continuous recreation. Each remembrance was not a replay of a fixed event, but a creative quantum negotiation that subtly transformed the remembered experience. Oral history traditions found new scientific validation. Indigenous storytelling practices, long dismissed as less reliable than written documentation, emerged as sophisticated quantum communication technologies that preserved historical information through complex quantum information transfer. Dr. Ilara Winters saw these discoveries as more than historical research. "We are learning," she would argue during intense research discussions, "that history is not a fixed narrative. It is a dynamic quantum process of collective human understanding." Archaeological research underwent a fundamental transformation. Quantum sensing technologies could detect historical interactions at molecular and quantum scales. Minute traces of human activity could now be read as complex quantum communications, revealing layers of historical experience previously invisible to traditional research methods. Collective trauma and historical memory found a profound scientific framework. Historical experiences could be understood as quantum probability fields, with traumatic events existing in multiple potential states of interpretation and understanding. Dr. Marcus Holloway continued to challenge these historical interpretations. "This is historical mysticism," he would thunder during academic conferences. "History requires objective, verifiable documentation." But the experimental evidence was becoming increasingly difficult to dismiss. Genealogical research took on new dimensions. Family histories emerged as complex quantum communication networks, with individual experiences interconnected in ways that transcended linear understanding. Quantum-informed historical methodologies suggested entirely new approaches to understanding human collective experience. Instead of viewing history as a fixed narrative, historical research became a process of quantum negotiation, exploring multiple potential historical trajectories. Cultural memory research revealed how collective experiences were transmitted through sophisticated quantum information transfer mechanisms. Historical understanding emerged not as a fixed record, but as a dynamic quantum dialogue of collective human potential. Language preservation technologies could now map the quantum nature of linguistic evolution. The transmission of cultural and historical information through language could be understood as a complex quantum communication process. Conflict resolution strategies found a new scientific foundation. Understanding historical conflicts as quantum probability fields suggested approaches that could explore multiple potential resolution trajectories simultaneously. Predictive historical modeling became possible through quantum probability mapping. Researchers could explore multiple potential historical developments, understanding history as a field of continuous potential rather than a fixed narrative. Dr. Elena Karoff captured the essence of these discoveries in her most profound statement. "We are not passive observers of history. We are participants in a continuous quantum dialogue of collective human experience." The boundaries between physics, history, and human experience were dissolving. Quantum mechanics was revealing that historical understanding was not a fixed system, but a living, breathing quantum ecosystem of extraordinary complexity and potential. As research continued, humanity stood on the brink of a profound revelation. Human history was not a linear progression, but a living, breathing quantum network of collective human potential. The universe was revealing its true nature, and nothing would ever be the same again. The exploration of quantum mechanics in educational systems represented a fundamental reimagining of human learning, transforming education from a process of information transfer to a dynamic, interactive dialogue of collective potential and discovery. Dr. Elena Karov's research facility had become a global center of educational quantum research, challenging every fundamental assumption about how humans learn, understand, and interact with knowledge. What had once been understood as a linear process of information transmission now emerged as a complex quantum network of collective cognitive potential. Dr. Antoinette Laurent had developed revolutionary quantum learning technologies that could map cognitive interactions at unprecedented scales. These quantum educational sensors revealed learning not as a passive absorption of information, but as an active, dynamic quantum process of continuous creation and potential. We are not just teaching students, Laurent would explain during groundbreaking educational conferences. We are engaging in a quantum dialogue of collective human potential. Each learning interaction is a negotiation, each moment of understanding a creative act of discovery. Dr. Wilhelm Kreutzer's mathematical models provided a theoretical framework for understanding educational systems as quantum probability networks. His equations suggested that learning was far more fluid, far more interconnected than traditional educational methodologies had ever conceived. Classroom environments were completely reimagined. Traditional fixed learning spaces gave way to dynamic quantum learning ecosystems. Classrooms became adaptive environments that could respond to the collective quantum state of students' consciousness, shifting and transforming to support individual and collective learning potential. Quantum-informed pedagogical approaches transformed the fundamental nature of education. Learning was no longer viewed as the transfer of fixed information, but as a dynamic quantum exploration of collective potential. Students were not passive recipients of knowledge, but active participants in a continuous quantum dialogue of discovery. Cognitive assessment technologies evolved beyond traditional testing methodologies. Quantum learning sensors could map individual and collective cognitive potential, revealing learning not as a fixed set of measurable outcomes, but as a complex probability field of human potential. Dr. Alara Winters saw these discoveries as more than educational research. We are learning, she would argue during intense research discussions, that education is not about filling empty vessels with information. It is a dynamic quantum process of collective human potential. Interdisciplinary learning became the fundamental approach. Traditional subject boundaries dissolved, replaced by quantum learning networks that explored knowledge as an interconnected field of potential rather than isolated domains of information. Artificial intelligence in educational technologies evolved from passive information delivery systems to sophisticated quantum learning explorers. AI could now support individual learning trajectories by mapping complex quantum probability fields of individual and collective cognitive potential Dr. Marcus Holloway continued to challenge these educational interpretations. "This is educational mysticism," he would thunder during academic conferences. "Education requires objective, measurable outcomes." But the experimental evidence was becoming increasingly difficult to dismiss. Neuroscience research revealed learning as a sophisticated quantum process. Cognitive development emerged not as a linear progression, but as a complex quantum negotiation of neural potential. Brain plasticity was understood as a continuous quantum dialogue of cognitive possibility. Quantum-informed special education strategies suggested revolutionary approaches to supporting diverse learning potentials. Learning differences were no longer viewed as deficits, but as unique quantum configurations of cognitive potential. Global educational exchange programs became sophisticated quantum dialogue platforms. Cultural learning could be understood as a complex quantum communication process, with knowledge transferring through intricate networks of human potential. Language learning technologies transformed learning from a mechanical process of memorization to a dynamic quantum exploration of linguistic potential. Students could now engage with language as a living, breathing quantum communication system. Creativity and innovation became central to educational approaches. Learning was understood as a continuous process of quantum potential exploration, with creativity viewed as a fundamental cognitive quantum mechanism. Collaborative learning technologies could map the quantum interactions of collective learning potential. Group learning emerged as a sophisticated quantum communication network, with knowledge emerging through complex collective interactions. Dr. Elena Karoff captured the essence of these discoveries in her most profound statement: "We are not transferring information. We are participating in a continuous quantum dialogue of human potential and discovery." The boundaries between physics, education, and human potential were dissolving. Quantum mechanics was revealing that learning was not a fixed system, but a living, breathing quantum ecosystem of extraordinary complexity and potential. As research continued, humanity stood on the brink of a profound revelation. Education was not a mechanical process, but a living, breathing quantum network of collective human potential. The universe was revealing its true nature, and nothing would ever be the same again. The culmination of quantum mechanical understanding represented more than a scientific breakthrough. It was a profound transformation of human consciousness, a fundamental reimagining of reality that touched every aspect of human existence. Dr. Elena Karoff stood in the research facility's central hall, surrounded by the pioneering scientists who had spent decades unraveling the fundamental nature of reality. The walls were covered with intricate diagrams, mathematical equations, and holographic representations of quantum interactions that seemed to breathe with their own mysterious life. Dr. Elara Winters, now in the twilight of her remarkable career, approached Elena with a look of profound understanding. "We are not at the end of a journey," she said softly. "We are at the beginning of a fundamental reimagining of human potential. The quantum revolution had transformed every domain of human understanding. What had begun as a series of seemingly impossible experimental observations had grown into a comprehensive reimagining of reality itself. Physics, biology, consciousness, art, economics, education. No field of human endeavor remained untouched by the quantum revelation. Dr. Antoinette Laurent reflected on their journey The quantum pioneers had discovered something far more profound than a scientific theory. They had uncovered a fundamental truth about the nature of existence, that reality was not a fixed stage, but a dynamic, interactive process of continuous creation. Dr. Wilhelm Kreutzer's mathematical models, which had once seemed like abstract theoretical constructs, now provided the foundational language for understanding reality's most fundamental nature. His equations revealed the universe as a complex, interconnected quantum network of infinite possibility. The quantum understanding challenged every fundamental assumption about human existence. Reality was not objective. Observation was not passive. Consciousness was not confined to individual beings, but a fundamental process of cosmic creation. Dr. Marcus Holloway, once the most vocal critic of quantum mechanics, now sat quietly in the corner. The scientific establishment that had fought so hard against these revolutionary ideas had been completely transformed. The quantum pioneers had not just discovered a new scientific theory. They had initiated a fundamental revolution in human understanding. The practical applications of quantum mechanics had reshaped human civilization. Quantum technologies had revolutionized computing, communication, medicine, energy production, and nearly every aspect of human technological capability. But these were mere surface manifestations of a deeper transformation. The true revolution was philosophical, existential. Quantum mechanics had revealed that humans were not passive observers of reality, but active participants in its continuous creation. Every observation was a creative act. Every moment of perception was a negotiation with the fundamental nature of existence. The boundaries between scientific disciplines had dissolved. Physics, biology, psychology, economics, art, these were no longer separate domains, but interconnected quantum networks of human potential. Dr. Elena Karoff understood the profound responsibility that came with this understanding. We are learning to speak the fundamental language of the universe, she would say. Each discovery is a conversation, each observation a creative act. The quantum pioneers had discovered something far more profound than a scientific theory. They had uncovered a fundamental truth about the nature of existence, that reality was a living, breathing ecosystem of possibilities. Consciousness emerged not as a product of brain activity, but as a fundamental quantum process of cosmic creation. Humans were not separate from the universe. They were the universe experiencing itself. The research facility had become more than a scientific laboratory. It was a sanctuary of human potential, a place where the fundamental nature of reality was being continuously negotiated and explored. Dr. Ilara Winters saw the broader implications. We are not at the end of scientific discovery, she would argue. We are at the beginning of a new way of understanding existence itself. Quantum mechanics had revealed that the universe was not a fixed, deterministic system. It was a dynamic, interactive process of continuous creation. Every moment was a negotiation of potential. Every observation was a creative act. The technological applications were profound, but they were merely the surface manifestation of a deeper transformation. Quantum technologies had reshaped human civilization, but the true revolution was in human understanding. Humanity was learning to speak the fundamental language of the universe. Each discovery was a conversation. Each observation was a creative act of cosmic participation. Dr. Elena Karoff looked around the room at her fellow pioneers. They had challenged everything humanity thought it knew about reality. They had revealed a universe far more strange, far more wonderful than anyone had ever imagined. As the afternoon light filtered through the laboratory windows, casting intricate patterns across the quantum diagrams, Dr. Karoff understood something profound. This was not an ending. This was a beginning. The universe was revealing its true nature, and nothing would ever be the same again. Up next, you've got two more standout theories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.